is nothing like your first lesson. There is nothing like your first lesson. It's one of the most exhilarating feelings you'll ever have in your life.
So what is flying all about? It's about art and science, imagination and invention. It's about challenge and adventure, determination and skill, exploration and discovery. Flying is about all these things and more. The flying experience is as unique as the many individuals who take up the challenge to pursue the dream of flight. You may be thinking about learning to fly for one or more of these reasons, or you may have an entirely different motivation. Whatever the reason, if you yearn to spread your wings and expand your horizons, this is your chance. You can learn to fly. Where do you begin?
As you begin your training, one of the first things you will become familiar with are the components of the airplane and how to use the different controls to make the airplane respond. When you sit in the cockpit of an airplane, you're actually sitting within the framework of the airplane. This framework is called the fuselage and is the attachment point for the other major components of the airplane. It also contains the passenger seating and baggage areas, as well as the cockpit. Within the cockpit are the flight controls and the instrument panel. Located on the panel are the flight instruments and engine gauges. The flight instruments are helpful for verifying your direction of flight, determining your airspeed, and indicating whether or not you're flying level, climbing, descending, making a turn, and your rate and coordination of turn. They also can show how fast you are climbing or descending, and your altitude. The engine gauges are important for monitoring engine performance. On most single-engine airplanes, the engine is mounted in the front of the fuselage. Aircraft engines are covered with a cowling, which streamlines the flow of air over the engine and directs the air around the cylinders for even cooling of the engine components. You control engine power by using a throttle located in the cockpit. The engine provides power to turn the propeller. In small airplanes, the engine and the propeller make up the power plant, which produces the force necessary to move the airplane through the air. This force is called thrust. The wings, working in conjunction with the power plant, not only produce the force called lift, which keeps the airplane in the air, but also contain the control surfaces which allow you to bank the airplane. These control surfaces are called ailerons and are located outboard on the trailing edge of the wings. When you rotate the control wheel to the right, the left aileron deflects downward, and the right aileron deflects upward. This moves the right wing down and the left wing up. The result is a bank to the right. How this is accomplished will be discussed in a later section. Attached to the aft end of the fuselage is the empennage, which contains the horizontal and vertical stabilizers. In addition to providing stability, the horizontal stabilizer contains the elevator. As the name suggests, the elevator controls the nose-up or down movement of the airplane. This is called pitch attitude. The elevator is controlled by the forward and aft movement of the control wheel. When you apply aft pressure on the control wheel, the trailing edge of the elevator deflects upward, producing a down force on the tail of the airplane. This in turn causes the nose of the airplane to pitch up. Forward pressure on the control wheel has the opposite effect. The trailing edge of the elevator is deflected downward, which pushes the tail up, causing the nose to pitch down. The rudder is the movable surface attached to the vertical stabilizer. It is controlled through the use of pedals located on the floor of the cockpit. Applying rudder pressure swings the nose of the aircraft left or right in a yawing motion. Your speed during flight varies according to what you wish to accomplish. For example, during an approach to a landing, it is better to fly at a slower airspeed. The use of flaps, located inboard on the trailing edge of the wings, helps you maintain this airspeed during the descent. Flaps are retracted or extended by a switch mounted on the instrument panel. Since there are times when using all of the flaps would be too much, most general aviation airplanes have 3 or 4 flap settings. All airplanes are equipped with some form of landing gear. The most common type found on training airplanes is the tricycle gear, with 2 main wheels and a steerable nose wheel. Steering is accomplished by moving the rudder pedals in the direction of the desired turn. Other aircraft may be equipped with 2 main wheels forward and a tail wheel. This type of aircraft has conventional gear. It is often referred to as a tail dragger. Seaplanes may use a hull-type fuselage or be equipped with floats for water operations. Higher performance aircraft have retractable gear, which improves their performance by streamlining the air flowing around the aircraft. No matter what type of gear is used, they all must be capable of absorbing the loads imposed by repeated landings and by taxiing over uneven surfaces. Brakes are also an integral part of the landing gear. They are activated by pressing individual toe brakes located on the top portion of the rudder pedals. Each brake can be operated independently of the other to reduce the turning radius during ground operations. However, you should avoid using the brakes for primary directional control because most of your turning can be achieved with the nose wheel steering alone. The parking brake can then be set by engaging the hand lever in the cockpit. What you have just viewed in this section is a brief overview of the airplane and some of its components. Your textbook goes into greater detail on these subjects and covers additional items which were not covered in the video.
In this section, we'll take a look at the parts of the airplane that provide the thrust necessary to sustain flight. In addition, while gaining a basic understanding of how the power plant operates, you'll learn how you, as a pilot, can monitor and control the engine and propeller. In many ways, the engine in an airplane is similar to the engine in your car. Both produce mechanical energy through a cycle which occurs within the cylinders. There are 4 strokes to every cycle: intake, compression, power, and exhaust. The first part of the 4-stroke cycle is the intake stroke. As the piston moves away from the cylinder head, the intake valve opens and a combustible fuel and air mixture is drawn into the cylinder. Next, the mixture is compressed as the intake valve closes and the piston moves back toward the cylinder head. When the compression stroke is almost complete, both spark plugs ignite the mixture. The combustion drives the piston away. This creates the power necessary to turn the crankshaft. Finally, the exhaust valve opens and the burned gases are forced out of the cylinder. In light training aircraft, this cycle repeats itself approximately 1,300 times a minute during cruise flight. The same cycle is taking place in each of the other cylinders. However, the sequence is staggered, so a power stroke is always being applied to the crankshaft. This provides you with a smooth-running engine. Since the crankshaft is connected to the propeller, its rotation causes the propeller to spin and produce thrust. The cylinders on an air-cooled engine are cast with thin fins, which increase the surface area. Heat from the cylinders passes into these fins and is carried away by the airflow around the engine. Now that you have a basic understanding of the engine, let's take a look at the various systems that help you monitor and control it. Let's begin by taking a look at how the engine receives the spark necessary to ignite the fuel and air mixture in the cylinders. The basic source of current is a magneto, which produces a hotter spark at higher engine speeds than does the battery system used in your car. The magneto fires as soon as you engage the starter and will continue to fire as long as the crankshaft is turning. There are actually 2 magnetos for each engine, which means the airplane has a dual ignition system. Since the 2 magnetos are independent of one another, each one fires a different spark plug in each cylinder. This makes it possible for the engine to run on either set, so that your engine will continue to run safely if one magneto or spark plug fails. Besides being a safety factor, having 2 spark plugs in each cylinder improves the combustion of the fuel and air mixture, resulting in more engine power. The airplane's ignition switch controls which magneto you're using. For example, after the engine starts, normal flight conditions require the use of both magnetos. Before you take off, however, you can test the independent performance of each side. Just how you perform this check will be discussed in the pre-takeoff checklist section of takeoffs and landings. When shutting down the engine, it's very important that you remember to turn the ignition switch off. If it is left in the right, left, or both position, the engine could still start if someone moves the propeller from outside the airplane. Turning off the master electrical switch without turning the magnetos off will not prevent the engine from starting, because the magnetos are separate from the rest of the aircraft's electrical system. To achieve the best performance from your engine, each cylinder must receive the proper fuel-air mixture. The engine induction system lets you regulate the proper mixture required during different flight conditions. Before the mixture enters the cylinder, a carburetor meters the correct amount of fuel and then combines it with filtered air. The carburetor, however, is calibrated to provide the proper fuel-to-air combination at sea level when the mixture control lever is set in the full rich position. But as you have learned, the density of the air decreases as you climb to higher altitudes. Subsequently, the density of the air entering the carburetor will decrease, while that of the fuel remains the same. This means that the mixture becomes too rich, or there is too much fuel for the density of the air entering the carburetor. A mixture control lever or knob is located in the cockpit. It enables you to adjust the amount of fuel to maintain the correct fuel and air blend at varying altitudes. If you fail to adequately lean the mixture as recommended in the pilot's operating handbook, the engine will run rough. An overly rich mixture causes a cooling effect in the cylinders. This can foul spark plugs and valves, resulting in a loss of power. On the other hand, if you lean the mixture too much, the engine temperature will become very hot. A mixture that's too lean can cause detonation and/or pre-ignition, which can damage or even destroy major components of the engine. Detonation is the explosive combustion of fuel in the combustion chamber, rather than the smooth burning that normally occurs. It can develop whenever you allow the engine to overheat. Besides occurring with an excessively lean mixture, it can also result from using an improper fuel grade. Other causes include taking off when the engine is near maximum allowable operating temperature, and flying with a high power setting and low airspeed configuration, which may not provide adequate engine cooling. A different form of abnormal combustion, preignition, is caused by a hot spot in the cylinder and occurs when the fuel and air mixture ignites prematurely. This hot spot may be a carbon deposit on a spark plug or any damage found around the combustion chamber. Another potential source of engine roughness and possible fuel starvation is carburetor icing. Because of the rapid cooling that takes place inside the carburetor when fuel vaporizes and the air expands, moisture can condense, freeze, and begin adhering to the internal surfaces. This accumulation of ice can substantially restrict or even cut off the fuel-air mixture to the engine. Although carburetor icing can occur over a wide range of conditions, it is most likely to form when the relative humidity is above 80% and the temperature is below 21 degrees Celsius or 70 degrees Fahrenheit. In most training airplanes with a fixed-pitch propeller, the first indication of carburetor ice and the subsequent power loss is a gradual decrease in engine RPM, which may not be readily noticeable. If this situation occurs, you should apply carburetor heat. This routes heated air into the carburetor to melt the ice. On some of the airplanes that you'll fly, a fuel injection system is used instead of a carburetor as a more precise way to meter the fuel and distribute the fuel-air mixture to the cylinders. Although fuel injection is typically a more expensive type of induction system, it has several advantages over a carburetor. These include a more even fuel distribution to the cylinders, which reduces operating temperatures, improved acceleration, and lower fuel consumption. The system is also less susceptible to induction icing. Although fuel injection has many benefits, you may experience some problems with the system, particularly when attempting to start a hot engine. The problems occur after shutting down the engine as the air temperature inside the tightly enclosed cowling increases. The temperature inside the induction system can reach a point where the fuel vaporizes, creating a vapor lock, which effectively blocks the fuel flow. Although the specific starting procedure varies, an auxiliary fuel pump is normally used to clear the fuel vapor and reestablish the fuel flow. Fuel vaporization can also occur during ground operations due to inadequate engine cooling, and you might have to use the fuel pump intermittently to purge the vapor lock and prevent fuel starvation. Whether you fly airplanes with a carburetor or fuel injection, engine efficiency decreases as you gain altitude, and thus the density of the air entering the engine is reduced. To overcome this drawback, some engines incorporate a turbocharger that compresses the air that enters the combustion chamber. This increases the density of the air. Ultimately, the airplane is capable of operating at higher altitudes, since the engine can continue producing sea-level power as you climb. During your pre-flight check, you should make sure the oil level is correct, because after the engine is running, the moving parts are lubricated by engine oil. This oil also helps to keep the internal temperature of the engine within acceptable limits. The heart of the oil system is the pump, which draws oil from the sump, pumps it through an oil filter and cooler, and then routes it to the engine. Gauges on the instrument panel display the oil pressure and temperature. A green region normally shows the correct oil pressure. If you observe an abnormal indication, you should assume that the engine parts are not receiving adequate lubrication. An oil temperature gauge lets you keep an eye on the system by displaying whether or not the temperature is in the permissible range. On many light airplanes, this gauge is the only indication of engine temperature. If the engine is running a little hot, you can assist in the cooling process by using a richer mixture setting, reducing your rate of climb, increasing airspeed, and reducing the power setting. The second part of the power plant is the propeller, which produces the thrust necessary to move the airplane through the air. The propeller consists of a hub and 2 or more blades. Since each blade is an airfoil, it is subject to the same aerodynamic factors that apply to any airfoil. The camber of a rotating propeller creates a lower pressure area in front of the blades, just like a wing creates a lower pressure area above the airfoil. This produces the horizontal lift or thrust necessary to propel the airplane through the air. However, unlike the wing, which is traveling at a uniform rate in straight and level flight, the tips of a propeller are traveling through the air faster than the area near the hub. Therefore, a propeller blade is twisted with less angle near the tips. This creates uniform thrust along most of its length. The overall angle of the blade determines its operating efficiency in various phases of flight. A propeller with a low blade angle is capable of producing more RPMs and is best suited for takeoffs and climbs. A blade with a high angle, however, is more efficient for cruise flight. Most light training airplanes use a fixed pitch propeller with an overall blade angle somewhere between a true climb propeller and one designed just for cruise. This provides relatively efficient thrust throughout the airplane's operating range. With a fixed pitch propeller, the blade's angle cannot be changed. On airplanes with a fixed pitch prop, you control engine power and propeller RPM solely through the use of a throttle. As you add power, the increase in engine and propeller RPM is indicated on the tachometer. Some airplanes use a more expensive constant speed propeller. With this type of prop, you can vary the pitch to obtain the most efficient blade angle during the different phases of flight. Airplanes with constant speed propellers have 2 power controls, the throttle and propeller control. As you adjust the throttle, the changing power output is indicated on a manifold pressure gauge. Manifold pressure is measured in inches of mercury and represents the pressure of the fuel and air mixture inside the engine's intake manifold. The higher the pressure, the greater the engine power being produced. By advancing the throttle, you increase the fuel and airflow to the combustion chamber and thus increase the manifold pressure. Since manifold pressure is measured in inches of mercury, the gauge is essentially an aneroid barometer. This means that when the engine is not running, the atmospheric pressure is displayed. The propeller control lets you change the pitch of the propeller blades, which regulates the RPMs shown on the tachometer. Your ability to select and maintain various blade angles and RPM settings for different phases of flight is where the efficiency of a constant speed propeller is measured. Changing propeller RPMs is much like changing the gears on an automobile or bicycle, where a low gear is best during acceleration and a high gear for cruise. For instance, before takeoff, you adjust the knob to set the propeller to a low blade angle. This provides high RPMs for maximum takeoff thrust. Upon reaching cruising altitude, you adjust the blades to a higher pitch. This produces a lower RPM and provides adequate thrust for cruising airspeed. Once you've selected the appropriate RPM, the propeller's pitch will adjust slightly during varying flight conditions so that the propeller load matches engine torque and the tachometer setting remains constant. Also, as you alter the manifold pressure with the throttle, the propeller will automatically adjust its pitch to maintain the selected RPM setting. Because the propeller can be very dangerous, exercise extreme caution when you're near an airplane. Even if the propeller isn't turning, the pilot in the airplane might be getting ready to start the engine. In addition, if you are flying with passengers, you should routinely brief them about the proper procedures to follow when around an airplane. The power plant installed in today's airplane is very reliable, but to get maximum use and consistent performance, you need to operate it in accordance with the procedures and specifications prescribed in the Pilot's Operating Handbook. Now that you have an understanding of how the power plant performs, let's take a look at how the engine is provided with fuel and examine the electrical system found on most training airplanes. Let's start with the fuel system. Generally, there are two types of fuel systems which you might encounter during your training. The first is the gravity feed type commonly found in high-wing airplanes. With this type of system, the fuel tanks are usually mounted inside the wings. Because of the difference in height between the tanks and the engine, gravity forces the fuel to the carburetor. A second type of system must be incorporated on low-wing airplanes, where the fuel tanks are positioned below the engine. Here, an engine-driven fuel pump supplies fuel from the tanks to the carburetor. However, this pump only supplies fuel once the engine is running. For starting, an electric boost pump is used to supply fuel. It can also be used as a backup should the engine-driven pump malfunction. No matter which type of fuel system your airplane uses, you must determine before each flight that your airplane has been filled with the proper amount of fuel. Always verify that the tanks contain the corresponding amount of fuel that was shown on the gauges. Never rely on the fuel gauges as your sole source of determining fuel quantity. You should also ensure that the tanks contain the correct type of fuel. Airplane engines are not all alike, and each one is designed to use a particular grade of fuel. To help with identification, colored dyes are added to each type. For example, 80 grade fuel is colored red, 100 low lead is blue, 100 is dyed green, and turbine fuel is colorless. The POH lists the acceptable fuel for the aircraft you're flying. If the proper fuel is not available, using the next higher grade of fuel for a short period of time is not considered harmful, as long as the manufacturer has authorized it. However, you should never use a lower grade because it can produce excessively high engine temperatures and cause serious engine damage. In addition, you should never use turbine or jet fuel in a reciprocating engine. Another consideration during pre-flight is to check for fuel contamination. You can do this by checking the wing tank drains and the fuel strainer. If you discover water or sediment, you should continue to drain the system to eliminate all traces of the contamination. One way to minimize water in the tanks is to make sure they are filled after the last flight. This helps prevent water vapor from condensing in a partially filled tank due to temperature changes during the night. Managing fuel consumption during your flight is equally as important as checking it before you take off. The fuel quantity gauges display the volume remaining in each tank. Besides showing the number of gallons, many also indicate the fuel's weight. To help you manage the fuel use efficiently, a selector valve is placed in the cabin, allowing you to select fuel from various tanks. While many airplanes have a selector valve that allows you to draw fuel from both tanks during normal operations, others necessitate switching back and forth from one tank to another. With this type of system, you need to avoid running on only one tank for an extended period of time, since the unbalanced fuel load will affect the airplane's stability. It's also essential that you follow the procedures outlined in the airplane's POH for changing tanks to ensure an efficient and uninterrupted fuel flow to the engine. Now let's turn our attention to how the airplane's electrical system provides the power to run the avionics and electrical equipment. Most modern airplanes derive electrical energy from an engine-driven alternator, which produces alternating current and converts it to direct current. The direct current is then delivered to a bus bar, which distributes the power to the various electrical equipment. This typically includes among other things, various lights, the radios, the turn coordinator, and gauges. Another critical component in the electrical system is the battery. Although its primary purpose is providing a means of starting the engine, it also can be used in an emergency to provide limited power to the electrical components. An ammeter mounted on the instrument panel measures the amount of current flowing to or from the battery. It provides you with the means of monitoring the electrical system. After the engine starts, the needle will deflect to the plus side to show that the battery power lost during the start is being replaced. Once the battery is charged, the needle will stabilize near zero to show you that the alternator is now supplying the current to the electrical system. If the needle begins pointing to the minus side, it means that the electrical load is exceeding the alternator's output capability and that the battery is helping to supply electrical power. A negative indication could also mean a malfunctioning alternator. If this occurs, you should reduce the electrical load by turning off non-essential equipment and land as soon as practical. The entire electrical system is controlled with a master switch. This switch is designed in such a way that the battery function can be activated without the alternator. But the alternator half cannot be activated independently. If you experience an alternator problem during flight, you can remove it from the electrical system by turning the alternator side of the switch off. Just remember that when doing so, you place the entire electrical load on the battery. In order to protect the various components from the possibility of an electrical overload, your airplane is equipped with fuses or circuit breakers. Normally, each component's name is printed on the circuit breaker panel. If an overload occurs, the circuit breaker will pop, protecting the various components within that circuit. After a short cooling period, you can reset the breaker by pushing it back in. However, if it pops again, an electrical problem probably exists, and the device should not be used until it is repaired. As with all of the airplane systems, a sound knowledge of how the fuel and electrical systems operate will help you to become a safer and more professional pilot. The aircraft POH will not only provide you with an abundance of information for normal operations, but will also detail the appropriate actions to take in the event of a system malfunction.
There are 6 basic flight instruments which are designed to provide you with the information you will need to control the airplane. Let's begin by looking at the pitot-static instruments. The pitot-static instruments include the airspeed indicator, altimeter, and vertical speed indicator. Because these instruments operate on the principle of pressure differential, you need to understand how the atmospheric pressure surrounding your airplane changes in various situations. For example, as you climb to a higher altitude, the density of air decreases. Therefore, the pressure of the air is lower. The pitot-static instruments are able to sense the changes in atmospheric pressure and provide you with information concerning your airspeed, altitude, and rate of altitude change. During flight, the pressure surrounding the airplane enters the instruments through a static port, which is positioned in an area of relatively undisturbed air, such as the side of the fuselage. At the same time, ram air pressure enters through a small hole at the front of a pitot tube, which is mounted so it is exposed to the relative wind. While all 3 instruments use the ambient air pressure provided by the static port, only the airspeed indicator uses ram air pressure from the pitot tube. The airspeed indicator displays the speed of your airplane through the air by measuring the difference between the ram air pressure entering the pitot tube and the ambient air pressure that enters the static port. As this pressure differential changes, the airspeed needle moves. A number of color-coded arcs are incorporated on the instrument face and represent various airspeed limitations. For example, the white arc shows the flap operating range. The upper end of the white arc indicates the maximum airspeed permissible with flaps fully extended, while the lower end shows the stall speed with full flaps. The white arc becomes very useful during the landing phase of your flight because it helps you determine when you can safely extend the flaps. It also shows you when you're approaching the normal stall speed in the landing configuration. Most of your flying, however, will occur at airspeeds within the green arc, which is known as the normal operating range. The lower boundary of this arc shows the airplane's stall speed when it's at the maximum takeoff weight with the flaps up, and, if applicable, the landing gear retracted. The upper limit of the green arc is the maximum structural cruising speed. You can exceed this airspeed and begin flying in the yellow range only when the air is smooth and only with caution. Finally, a red marking is placed at the never exceed speed. You should never operate above this speed because structural damage could occur. During your flying, you will become familiar with several types of speed. For example, indicated airspeed is read directly from the instrument. However, when calculating airplane performance, you should use calibrated airspeed, which is indicated airspeed corrected for instrument and installation errors. You can determine calibrated airspeed by referring to the table provided in the pilot's operating handbook. True airspeed is your actual speed through the air. It is calibrated airspeed corrected for density changes due to altitude and non-standard temperatures. Another term, ground speed, describes your actual speed over the surface. In a no-wind situation, true airspeed, or TAS, and ground speed, GS, are equal. A headwind, however, will decrease your ground speed. Conversely, a tailwind will increase it. Now let's look at how the altimeter works to provide you with altitude information. The altimeter senses pressure changes in the surrounding atmosphere and converts this information to a display of your altitude. Most altimeters have 3 pointers. The longest shows hundreds of feet, the middle-sized pointer, thousands of feet, and the shortest one shows tens of thousands of feet. To properly read an altimeter, you must first look at the shortest pointer. In this case, it's between 0 and 1, indicating you're below 10,000 feet. The middle pointer shows that you're somewhere between 5,000 and 6,000 feet. And the longest pointer shows you're halfway between 700 and 800 feet. Putting the 3 together, you come up with an altitude of 5,750 feet. Be very careful when reading an altimeter because misreading it could lead to serious consequences. The altimeter also has a barometric scale which can be adjusted to compensate for variations in atmospheric pressure. Here you can see the numbers 29.9 and 30.0. You read these by adding a 0 to each number to get 29.90 and 30.00 inches of mercury. The barometric setting on this altimeter is read as 29.95 since the pointer is halfway between 29.9 and 30.0. As you can see, the distance between the printed numbers represents 1/10 of an inch of mercury. Since the barometric pressure changes approximately 1/10 of an inch for every 100-foot change in altitude, moving the scale 1/10 of an inch will cause the pointers to move 100 feet. Altimeter settings are provided by FAA facilities such as control towers and flight service stations. Before every flight, you should adjust the altimeter to the current reported setting. If you set it correctly, your altimeter should read the field elevation. Then during your flight, especially if you're leaving the local area, you should periodically adjust the altimeter to the latest reported setting. Let's see what might happen if you fail to make these adjustments. Suppose you're maintaining an altitude of 5,500 feet, and you're flying into an area of lower pressure. The altimeter interprets the decreasing pressure entering the static port as a climb, although you're actually flying level. When you notice the altitude gain, you will naturally lower the nose to descend to your desired altitude. However, in this situation, you will actually be descending to a lower altitude, even though the altimeter shows a return to 5,500 feet. To a certain degree, this same situation occurs when you're flying from an area of warmer air to one with cooler air. Obviously, this could be dangerous if you're flying over obstacles or high-rising terrain. It could also place you far off your appropriate VFR cruising altitude. A helpful memory aid to assist you in determining whether you're higher or lower than before is the phrase, "When flying from high to low or hot to cold, look out below." This means that in these situations, you're going to be below the altitude indicated on your altimeter. The best way to minimize this type of error is to periodically reset your altimeter to the current setting as reported by the nearest FAA facility. Keep in mind that an altimeter measures altitude above a specific reference. There are various types of altitudes depending on which reference you are using. For example, indicated altitude is read directly from the instrument. If the proper barometric pressure is set in the altimeter, its indication will be based on a standard plane called mean sea level, or MSL. In other words, if your altimeter is reading 2,000 feet MSL, you are actually flying 2,000 feet above this standard sea level reference. The distance between your airplane and sea level is called true altitude. If you're flying over a surface higher than mean sea level, you must subtract its height from the altimeter reading to obtain your distance above the surface. This difference is called absolute altitude and is often referred to as height above ground level, or AGL. Pressure altitude is referenced to a standard level of 29.92 inches of mercury. It is used with the existing temperature to determine density altitude. Density altitude is pressure altitude corrected for non-standard temperature. It is not really an altitude, but is a theoretical value used in the computation of aircraft performance. Now let's take a look at the last pitot-static instrument, the vertical speed indicator. Like the altimeter, it is connected only to the static port. As you climb or descend, the VSI measures how fast the ambient pressure is changing and displays the rate of altitude change in feet per minute. In this situation, you're descending at 300 feet per minute. One of the most valuable uses of the VSI is that it immediately provides you with trend information when you begin to gain or lose altitude. After a few seconds, the VSI stabilizes and displays the actual rate of altitude change. Although the pitot-static instruments provide you with essential flight information, you need to use them in conjunction with the other instruments to precisely control your airplane. Gyroscopic instruments give you information about your airplane's attitude, its rate of turn, and its heading. These instruments include the attitude indicator, the turn coordinator, and the heading indicator. Before we take a look at the information these instruments provide, you need to understand how they operate. The primary element of each gyroscopic instrument is a heavily constructed spinning gyro mounted in gimbals. If the gyro is freely or universally mounted, it will remain in a fixed position no matter where you move its base. This degree of stability is known as rigidity in space. If the gyro is mounted in an instrument so the airplane can rotate about it, the aircraft's movements will be displayed on the instrument face. Most small airplanes use two different sources of power to spin the gyros. Typically, the turn coordinator uses electrical power, while the attitude indicator and heading indicator are driven by a vacuum system. By using two independent sources of power, you will still have some degree of backup should one system fail. A vacuum or suction gauge is normally positioned on the instrument panel to allow you to monitor the vacuum pressure. If the pressure is not at an adequate level, the gyro instruments could be unreliable. Now let's take a closer look at the attitude indicator. This instrument senses rolling and pitching movements, providing you with a pictorial view of your airplane's attitude in relation to the natural horizon. The attitude indicator uses a miniature airplane and an artificial horizon to show both angle of bank and pitch. The artificial horizon is controlled by the spinning gyro. Index markings are incorporated to show you precisely how much pitch and bank you're using. An adjustment knob enables you to align the miniature airplane with the horizon bar before takeoff and during straight and level flight. As you enter a level left turn from straight and level flight, the attitude indicator will detect and display the change in bank. In this situation, you are maintaining 30 degrees of bank. As you roll back to wings level, the attitude indicator will give you the same indication as the actual horizon. When you enter a descent from straight and level by lowering the nose, the instrument again displays your position in relation to the actual horizon. A combination of pitch and bank is shown just as easily. For example, during a climbing right turn, the nose is above the horizon, and the miniature airplane is banked to the right. Now let's take a close look at the information displayed by the electrically driven turn coordinator. The turn coordinator is actually two separate instruments. One instrument contains a spinning gyro which senses rolling and yawing movement. A miniature airplane on the face of the instrument represents the actual airplane and indicates your turn rate. For example, as you roll into a right turn, the miniature airplane will bank in the same direction, showing you how fast you rolled into the turn. Once the turn is established, it indicates how fast you're making the turn. It does not, however, show your actual bank angle. During certain maneuvers, you will be required to perform a standard rate turn, which is a turn rate of 3 degrees per second. This means that you'll be turning 180 degrees in 1 minute, or making a complete 360-degree turn in 2 minutes. When the miniature airplane's wing is aligned with the lower index mark, you're in a standard rate turn. The second part of the turn coordinator is the inclinometer, commonly referred to as the ball. It consists of a curved glass tube containing a ball that moves in response to gravity and turning forces. The ball is used to establish and maintain coordinated flight. For example, during straight and level coordinated flight, the force of gravity causes the ball to settle in the lowest part of the tube. During a coordinated turn, the ball will still remain centered between the reference lines. However, if the bank becomes too steep for the turn rate, the ball will move to the inside of the turn and indicate a slip. If the bank is too shallow for the turn rate, the ball will move to the outside of the turn, indicating the airplane is in a skid. You can center the ball by varying your angle of bank, or by applying rudder pressure in the direction of the deflected ball. To help you determine which rudder pedal to press, use the saying, "Step on the ball." In other words, if the ball is out to the right, step on the right rudder pedal. The final gyroscopic instrument is the heading indicator, sometimes referred to as the directional gyro. Like the attitude indicator, it receives its power from the vacuum system. The heading indicator is a relatively simple instrument to read. The graduations on the face are spaced at 5-degree intervals, with the cardinal headings north, east, south, and west marked with a letter. Between the cardinal headings, each 30-degree increment is marked by a number with the last 0 omitted. This instrument is showing a northwesterly heading of 330 degrees. Because the heading indicator does not have a magnetic north-seeking element, you will have to set it prior to each flight. You will also need to reset it during flight to counteract gyroscopic precession. The instrument to use when resetting the heading indicator is the magnetic compass. Since it is not a gyroscopic instrument, it will not experience the same errors which occur in a heading indicator. In addition, because it doesn't require any power, it is an important backup source for heading information. However, a magnetic compass does have its own limitations, which you should be familiar with when using it for directional information. For example, when a compass is mounted in an airplane, metals and electrical equipment produce local magnetic disturbances, resulting in a slight error in the indication. This error is called deviation. A correction card is mounted near the compass so you can correct for any deviation. For example, in this airplane, if you want to fly a magnetic heading of 090, you'll need to fly a compass heading of 088 degrees. The compass is also affected by magnetic dip, which is the tendency of a compass to point down and toward the magnetic poles. This error is greatest when you're near the poles. As a result of magnetic dip, your compass will give an incorrect reading when you turn, accelerate, or decelerate. In the northern hemisphere, a turn from a northerly heading results in the compass initially indicating a turn in the opposite direction, then lagging behind the actual heading. This lag decreases as you approach an easterly or westerly heading. In a turn from south, the compass will indicate the proper turn, but will lead the actual heading. As in a turn from north, this error diminishes as the turn approaches east or west. Errors also occur when you're accelerating or decelerating, especially if you're flying on an east or west heading. When you accelerate, the compass will indicate a turn to the north, even though you're still flying straight and level. The opposite is true when decelerating. In this case, the indication will be toward the south. A simple memory aid to help you remember which way the compass will move is ANDS, which stands for accelerate north, decelerate south. When you use the magnetic compass to reset the heading indicator, remember these limitations and reset it only when you're flying in straight and level, unaccelerated flight. Once you've achieved the ability to use and interpret the flight instruments correctly, you should be able to control your airplane with more precision. This will make your flying easier and make you a more proficient pilot.
Have you ever wondered what makes an airplane fly? There are 4 forces acting on an airplane in flight. These forces are lift, weight, thrust, and drag. The study of these forces and their role in flight is known as aerodynamics. Let's take a look at how these forces work together to achieve straight and level, unaccelerated flight. This means that the airplane is not turning, climbing, descending, or changing airspeed. It should be fairly clear that before an airplane can fly, lift must be created. Lift is the upward force created by the effect of airflow as it passes over and under the wing. Weight is the force that opposes lift and is caused by the downward pull of gravity. Thrust, created by the power plant, propels the airplane forward through the air, while drag, a retarding force, opposes thrust and limits the speed of the airplane. In unaccelerated flight, where thrust and drag are equal, the airplane will not speed up or slow down. Like thrust and drag, when lift and weight are equal, the airplane will not climb or descend. To help you understand lift, let's take a look at the basic principles of motion. In the 18th century, Daniel Bernoulli expanded on Sir Isaac Newton's laws of force and motion to describe the principle of airflow pressure differential. Observing what happened to air as it passed through a tube, Bernoulli discovered that as the velocity of a fluid or gas increases, its pressure decreases. He also found that with a constant velocity, the pressure of the air remains the same at both ends of the tube. If a constriction is placed in the middle of the tube, the same amount of air has to pass through a smaller area. This increases the velocity and decreases the pressure. If you were to replace the constriction with an airfoil, such as a wing, the same principle would still apply. As oncoming air meets the leading edge of the airfoil, it separates with part of the airflow going over the top and part going below. Since the air flowing over the top has farther to go, it must travel faster. The result is lower air pressure above the wing. This is a component of total lift. The remaining lift is provided by the downward-backward flow of air generated from the top surface of the wing. The lift provided by this flow can be explained by Newton's third law of motion, which states that for every action, there is an equal and opposite reaction. The reaction to this downwash results in an upward force on the wing and an increase in total lift. Before we look at various airfoils and how they are configured to take advantage of the laws of motion and principles of lift, let's look at some of the terminology. A line drawn from the leading edge to the trailing edge of an airfoil is referred to as the chord line. The camber of an airfoil is the curve of its surface. On general aviation training aircraft, the upper camber is usually more pronounced than the lower camber. Any object moving through the air encounters a relative wind. This wind is always parallel to and opposite the flight path. The angle formed between the relative wind and the chord line is called the angle of attack. A way to measure lift as it relates to angle of attack is the mathematical expression coefficient of lift, or CL, which is determined by wind tunnel tests and is based on the design of the airfoil. Each airplane has an angle of attack where maximum lift occurs. This point is known as CL max. Beyond this point, the airflow begins to separate from the wing's surface, becoming so turbulent that the airfoil can no longer create lift. At this point, the wing is in a stalled condition. The amount of lift that a wing can produce depends on several factors. One of these factors is wing design, which includes the shape or plan form of the wing. A straight wing has good slow flight characteristics, but is not structurally efficient in terms of lift and drag. A swept back or delta wing is much better at higher speeds. The tapered wing, on the other hand, has good slow flight characteristics and has a relatively efficient design. Another wing design factor is the aspect ratio, or the relationship between the wing's length and width. The aspect ratio can be found by dividing the wingspan by the average chord. In this example, the wing has an aspect ratio of 9. At a given angle of attack, the larger the aspect ratio, the less drag produced for the same amount of lift. General aviation training aircraft, for instance, normally have aspect ratios of 7 to 9, while gliders are usually between 20 and 30. Another design factor that affects a wing's flight characteristics is the angle of incidence. In this case, the wing is attached to the fuselage with the chord line inclined upward at a slight angle. You, as a pilot, can control lift by changing individually or in combination the airplane's airspeed, its angle of attack, and the wing configuration, such as lowering the flaps. If all other factors remain constant, doubling an airplane's airspeed develops 4 times more lift. This increase, however, is not without its drawbacks, since any increase in lift also results in an increase in drag. In addition, with all other factors remaining constant, an increase in angle of attack increases lift. For lift to remain constant, airspeed and angle of attack must be used in conjunction with each other. If airspeed increases, you must decrease angle of attack. Conversely, if you want to maintain the same amount of lift at a slower airspeed, you must increase the angle of attack. Another way of controlling lift is by changing the configuration of the wing. Lowering the flaps can increase the lifting efficiency of the wing and decrease the airspeed at which the airplane stalls. As flaps extend, they change both the camber and the chord line of the wing in the area of the flaps. This not only produces lower pressure above the wing due to the change of camber, but it also changes the wing's angle of attack. Suppose that with the flaps up, the angle of attack is 5 degrees. By lowering the flaps, which changes the chord line, the angle of attack increases to 10 degrees. This higher angle of attack provides more lift and more drag. Weight, like lift, is not a constant. It varies with the equipment installed in the airplane, the number of passengers, the amount of cargo, and the fuel load. During the course of a flight, the total weight of the airplane will decrease as fuel is consumed. In some specialized flight operations, such as crop dusting, firefighting, or skydiving, an additional reduction of total weight will occur. The forward-acting force which opposes drag and propels the airplane is thrust. The same physical principles involved in the generation of lift apply when describing the force of thrust. The thrust necessary to overcome drag and propel the airplane through the air is produced by the power plant turning the propeller. If you look closely at a propeller, you will notice that it looks like a twisted airfoil. As the propeller turns, a lower pressure area is created in front of each rotating blade. The low pressure in front of the propeller, like that above the wing, provides lift which acts forward. This forward-acting lift, or thrust, moves the airplane forward. During unaccelerated flight, where the airplane is neither increasing nor decreasing in airspeed, thrust and drag are equal. However, thrust may be increased by using the throttle to increase power. When you increase power, thrust will exceed drag, causing the airplane to accelerate. With this acceleration, however, there is a corresponding increase in drag. Drag will continue to increase until it is equal to thrust. When these two forces are in equilibrium, the airplane will stop accelerating and maintain the new higher airspeed. The force acting in the opposite direction to thrust is drag. There are two types of drag: parasite and induced. Parasite drag includes all the drag not directly related to the production of lift. It is generated by those areas of the airplane which disrupt the otherwise streamlined flow of air. These include items protruding into the airflow, such as the landing gear, rough surfaces, and the mixing of the air, such as where the wing joins the fuselage. As the speed of an airplane increases, the effects of parasite drag also increase. In contrast, induced drag is a direct byproduct of lift. It is greatest at slow speeds with a high angle of attack. Conversely, at higher speeds and at lower angles of attack, induced drag decreases. If the two drag curves are combined and the values added together, we can find a point where drag is at a minimum. This point is known as L over D max, which is where lift, when compared to drag, is at its greatest. In later sections, you will see that flying the airplane at this speed provides the best glide ratio and other performance benefits. The phenomenon known as ground effect occurs when the Earth's surface interferes with normal airflow patterns, thus causing a reduction in induced drag. During flight at altitudes, the downwash created by wingtip vortices causes the average relative wind to be inclined downward. Because lift acts perpendicular to the average relative wind, total lift is inclined aft by the same amount. The component of lift acting in a rearward direction is induced drag. As your airplane descends to within one wingspan of the ground, the wingtip vortices and resulting downwash are deflected horizontally. This in turn moves the average relative wind closer to the horizontal and the total lift vector closer to vertical, thus increasing the vertical component of lift and decreasing induced drag. As a result, the airplane tends to fly longer in ground effect or float down the runway. This can be a problem on shorter runways. Another problem occurs during takeoff, where you may lift off in ground effect at a very slow airspeed. If your airplane hasn't accelerated to a safe climb speed before climbing out of ground effect, the airplane could settle back to the runway. The information presented in this section has provided you with a fundamental knowledge of the forces at work on the airplane during straight and level, unaccelerated flight. The next section will expand your knowledge of what happens to the four basic forces during maneuvering flight. Throughout the years, aircraft engineers have worked to design airplanes which exhibit favorable stability characteristics. Stability can be defined as a design characteristic that causes an airplane to return to steady flight after being disturbed. In any discussion of stability, two kinds must be considered: static and dynamic. Static stability is the initial tendency displayed by an object after it is disturbed from equilibrium. Let's use a marble to demonstrate static stability. When the marble is resting at the bottom, it is in equilibrium. If it is disturbed, its initial tendency is to return to its original position. This tendency is referred to as positive static stability. How an object responds over time, as opposed to its initial reaction, is called dynamic stability. An airplane with both positive static and positive dynamic stability does not immediately return to its original attitude after displacement. Generally, it goes through a series of progressively smaller oscillations. Since an inherently stable platform is highly desirable, a training aircraft is normally designed to exhibit both positive static and dynamic stability. To understand how this is accomplished, we must look at stability in relation to the center of gravity and three axes of flight. Since an aircraft operates in a three-dimensional environment, aircraft movement takes place around one or more of the three axes of rotation. They are called the longitudinal, lateral, and vertical axes of flight. The common reference point for the three axes is the airplane's center of gravity, or CG, which is the theoretical point where the entire weight of the airplane is considered to be concentrated. Since all three axes pass through this point, you can say that the airplane always moves about its CG, regardless of which axis is involved. The ailerons, elevators, and rudder create aerodynamic forces which cause the airplane to rotate about the three axes. When an airplane is banked, it rolls about the longitudinal axis. For a right bank, you rotate the control wheel to the right. This moves the left aileron down and the right aileron up. A closer look at the outboard section of the left wing reveals that as the left aileron moves down, the angle of attack and the camber increase. This produces more lift on the left wing. Conversely, as the right aileron moves up, the angle of attack and the camber decrease, which produces less lift. This difference in lift between the left and right wings causes the airplane to roll about the longitudinal axis. This roll will continue until you return the control wheel to the neutral position. At this time, the lift created by the wings will again be balanced. the airplane will remain in a banked attitude until you move the control wheel to the left. This reverses the process and creates a roll back toward wings level. Moving the control wheel fore and aft moves the elevator or stabilator and creates a pitching movement around the lateral axis. When the control wheel is moved forward, an upward force is created on the elevator, which pitches the nose down. Moving the control wheel aft will create a downward force on the elevator, which in turn will cause the nose of the aircraft to pitch up. The swinging movement of the nose to the left and right is called yaw and occurs about the vertical axis. This rotation is controlled by the rudder. When you step on the right rudder pedal, for instance, the rudder deflects to the right, which creates an aerodynamic force to the left. This causes the nose of the airplane to yaw to the right. Keep in mind that the rudder is not used to turn an airplane in flight. Its primary function is to align the fuselage with the direction of flight. Now let's look at stability about the lateral axis, which is called longitudinal stability. Longitudinal stability is normally obtained by locating the center of gravity ahead of the center of pressure, which is the point along the wing chord where lift is concentrated. This creates a slight nose-heavy condition. To balance this condition, a tail-down or nose-up force is created by installing the horizontal stabilizer with a slightly negative angle of attack. If your airplane pitches up because of a gust of wind or momentary control deflection, the horizontal tail surface moves toward a neutral or slightly positive angle of attack. This decreases the tail-down force, and because the nose-heavy condition is no longer balanced, the nose will return to the trimmed condition. Similarly, if the airplane pitches nose down, the negative angle of attack, and in turn, the tail-down force increases. This tends to return the airplane toward its trimmed attitude. Additional downward forces are imposed on the horizontal surfaces by the downwash created by the propeller and wings. This means that as you reduce power, the tail-down force decreases, allowing the nose to pitch down. Conversely, when you add power, the tail-down force increases and the nose tends to pitch up. Although a certain amount of pitch change with an increase or decrease in power is considered desirable, too much change would unnecessarily increase pilot workload. To help compensate for this, aircraft designers frequently raise the engine thrust line slightly above the center of gravity. This creates a nose-down pitching force when power is added and somewhat offsets the increase in tail-down force caused by additional downwash. Since pitch stability depends upon the difference in location between the center of gravity and the center of lift, the CG's location obviously plays an important role in how an airplane handles. By paying close attention to where and how much fuel, cargo, and people you load on an airplane, you can ensure that the center of gravity will remain within the limits set by the manufacturer. If too much weight is loaded in the front section of the airplane, the CG will be forward of the limit, making the airplane nose-heavy. If this happens, there may not be enough elevator or stabilator force available to rotate the airplane for takeoff, or to raise the nose of the airplane during the landing flare. A potentially worse situation occurs when an airplane is loaded with the CG aft of the approved range. In this case, the airplane will be very unstable in pitch. Even with full forward pressure on the control wheel, recovery from a stall might not be possible. Stability about the longitudinal axes is called lateral stability. Positive lateral stability is the tendency of an airplane to roll back toward a wings level attitude following displacement by a gust of wind or inadvertent control movement. The most common design feature used to attain positive lateral stability is wing dihedral, which is the upward angle of the wings with respect to the horizontal. When an airplane with wing dihedral is displaced in a roll, it will immediately begin to slip in the direction of the lower wing. This creates a higher angle of attack on the low wing, which in turn increases the lift on that wing, resulting in a tendency to roll the airplane back toward wings level. Stability about the yaw axis is referred to as directional stability. When an airplane yaws to the right or left, the large surface area that is behind the center of gravity acts like a big weather vane. This forces the nose of the airplane back toward the original position. So far, we have examined stability with respect to the axes of the airplane. Now let's take a look at some factors relating to the recovery from stalls and spins. It is important to remember that an airplane can stall at any attitude and any airspeed. However, there are other factors which can affect stall speed, such as weight and environmental conditions. As aircraft weight increases, more lift must be produced to support the increased weight. In order to maintain the same airspeed, a higher angle of attack is required to produce the lift necessary to support the increased weight, which in turn causes an increase in the aircraft's stall speed. How you distribute the weight also can have a significant impact on stall speed. For example, a forward CG shifts the balance of the airplane, causing a nose-heavy condition. To counteract this and balance the airplane, tail downforce must be increased. You can do this by increasing the angle of attack, which causes an increase in tail downforce, as well as a corresponding increase in lift and stall speed. Environmental factors such as snow, ice, or frost, which have accumulated on the surface of the wings, can also cause an increase in stall speed by altering the shape of the wing and disrupting the airflow over the wing. The additional weight and drag also causes an increase in the stall speed. Another environmental factor that can affect stall speed is turbulence. The rapid vertical gusts associated with turbulence can cause abrupt changes in the direction of the relative wind and can result in an increase in the angle of attack. Regardless of what causes a stall, you should be able to recognize the indications of an impending stall and take appropriate action to initiate a recovery before it occurs. Most modern airplanes are equipped with a stall warning device, which gives you a warning a few knots before a stall occurs. As the stall approaches, the flight controls will feel mushy. Just before the stall occurs, you will feel a buffeting or vibration. In addition, you may notice a pitching motion as well as a sensation of decreasing airspeed or a sinking feeling. To recover from a stall, lower the nose toward the horizon to decrease the angle of attack and regain lift. Simultaneously, smoothly apply maximum allowable power to minimize altitude loss and increase airspeed. As the airspeed recovers, you should maintain coordinated flight while adjusting power to a normal level. Keep in mind, the reason you practice stalls is not to become proficient at stalling the airplane. Rather, it is to learn to recognize the signs of an impending stall and recover before the airplane reaches a fully stalled condition. The characteristic corkscrew flight path results from an uncoordinated stall where the aircraft's wings are unequally stalled. The three phases of a spin are incipient, fully developed, and recovery. The incipient spin is the portion of the stall when rotation begins, to the moment when the spin has stabilized and the flight path is nearly vertical. At this point, the spin is fully developed. The final phase is spin recovery. To initiate the recovery, retard the throttle and neutralize the ailerons. Then reference your turn coordinator to determine the direction of rotation and apply full rudder opposite the direction of the turn. Now you should briskly move the yoke forward to approximately the neutral position. Depending on the airplane, you may need to move the yoke to a full forward position. As the rotation stops, neutralize the rudder and gradually apply back pressure to return to level flight. During the recovery, you should pay close attention to your aircraft's airspeed and load limits. It's important to understand that as an applicant for a private pilot certificate, you are not required to demonstrate flight proficiency in spin entries or spin recovery techniques. The emphasis in spin training is to provide you with an awareness of the conditions that could lead to an unintentional spin, as well as the general recovery procedures.
Although aircraft may differ in design and performance, the aerodynamic forces acting on any maneuvering aircraft are basically the same. An understanding of the aerodynamics of maneuvering flight will help you develop the skill to perform precise maneuvers while operating your airplane within its design limitations. In straight and level unaccelerated flight, the forces acting on your airplane are in equilibrium. In a stabilized climb, the forces are also in equilibrium. However, the relationship between these forces is changed. When pitch is increased and the flight path is inclined, the force of weight is divided into two components. One component of weight opposes lift 90 degrees to the flight path, and another component acts in the same direction as drag, opposing thrust. Thrust also is divided into separate components, one which acts parallel to the flight path and the other which acts perpendicular to the flight path. The total thrust required is greater in a climb than in straight and level flight. Unless thrust is increased through an addition of power, airspeed will decrease as the pitch attitude increases. To maintain the airspeed, the transition from level flight to a climb normally requires a change in both pitch and power. Once pitch attitude is established and power is properly set, the airspeed and rate of climb will stabilize. During high-power, low airspeed flight conditions, such as those present in a climb after takeoff, several forces can act to create a noticeable left-turning tendency in propeller-driven aircraft. One of the forces, known as torque, is simply Newton's third law at work. For every action, there is an equal and opposite reaction. The force required to spin a propeller clockwise, as viewed from the cockpit, acts on the rest of the airframe as a force in the opposite direction. In other words, the airframe will rotate counterclockwise or to the left about the longitudinal axis. Gyroscopic precession also causes a left-turning tendency. The aircraft's propeller exhibits the same characteristics as a gyroscope: rigidity in space and precession. Precession produces a left-turning tendency and is most noticeable when the nose is pitched down, such as when a conventional gear aircraft raises its tail wheel during the takeoff roll. As the nose of the aircraft pitches down, a force is applied to the top of the propeller arc. This results in a force exerted 90 degrees in the direction of the propeller's rotation and causes the aircraft to yaw to the left. Another left-turning tendency, known as asymmetrical thrust, or P factor, is most pronounced when the engine is operating at a high power setting and the airplane is flown at a high angle of attack. When the propeller's plane of rotation is perpendicular to the relative wind, the ascending and descending propeller blades have equal angles of attack and produce equal amounts of thrust. As the airplane pitches to a high angle of attack, the descending blade of the propeller has a higher angle of attack than the ascending blade. The result is that more thrust is produced by the descending blade on the right side of the airplane, causing a turn to the left. Spiraling slipstream, which also produces a left-turning tendency, is the result of the airflow behind the propeller moving rearward in a corkscrew motion around the fuselage. Since the propeller is rotating clockwise, the slipstream pushes the vertical stabilizer to the right, causing the nose of the airplane to yaw left. To help counteract left-turning tendency and make the airplane easier to control, some manufacturers have incorporated special design features. One such feature is a small metal tab positioned on the trailing edge of the rudder. The tab is bent slightly to the left, so the pressure of the passing airflow pushes on the tab, forcing the rudder to the right. This creates a yawing moment, which counteracts the airplane's tendency to turn left. In stabilized descending flight, like a stabilized climb, the aerodynamic forces acting on the airplane are in equilibrium. However, during a descent, one component of weight acts perpendicular to the flight path, opposing lift, while the other acts forward along the flight path, adding to thrust and opposing drag. If the power setting is unchanged, airspeed increases as the nose is lowered in a descent, and a corresponding increase in parasite drag works to balance the force of weight. When airspeed stabilizes, aerodynamic forces are again in equilibrium. If the force of thrust is removed by reducing the power to idle, the forward component of weight must be increased to counteract the force of drag. In order to maintain the same airspeed, the nose must be lowered even further. In a gliding descent, the best glide angle and the best glide distance result from flying the airplane at an angle of attack which provides the least amount of total drag for the corresponding lift. This angle of attack is referred to as the maximum lift-to-drag ratio, or LD max. The aircraft's best glide speed normally is achieved at the angle of attack corresponding to LD max. The best glide speed is published in the pilot's operating handbook. For example, the best glide speed for this airplane at 2,600 pounds is 75 knots with the propeller windmilling, flaps and gear up in calm wind conditions. Glide ratio represents the distance an airplane will travel forward without power in relation to altitude loss. For example, a glide ratio of 10:1 means an airplane will travel approximately 10,000 feet of horizontal distance for every 1,000 feet of altitude lost in a descent. The angle between the flight path and the horizon is called the glide angle. As drag increases, so does glide angle. For example, in a glide when the landing gear is lowered, there is a corresponding increase in drag. To maintain the same airspeed, this increase in drag is counteracted by lowering the nose of the airplane, thus increasing the glide angle, which results in a reduced glide distance. Although the weight of the airplane doesn't affect glide ratio, it does affect the airspeed that must be flown to attain the best glide distance. Since a heavier airplane will sink faster, a higher airspeed must be maintained to support the greater weight and yield the same glide distance as a lighter airplane. Turning flight introduces new concepts with respect to the aerodynamic forces acting on the airplane. In a bank, total lift is divided into two components. One acts vertically to oppose weight, and the other acts horizontally to move the airplane in the direction of the turn. Since the vertical component of lift is reduced in a turn, to maintain altitude you must apply back pressure on the yoke to increase the angle of attack until the vertical components of lift and weight are again equal. The horizontal component of lift creates centripetal force, which acts toward the center of rotation. During the turn, this center-seeking force works to oppose inertia, which is the tendency of the airplane to continue in a straight line. As the airplane enters a turn, the aileron on the inside of the turn is raised, and the aileron on the outside of the turn is lowered. The lowered aileron increases the angle of attack and produces more lift for that wing. Since induced drag is a byproduct of lift, the outside wing also produces more drag. This increase in drag causes a yawing tendency toward the outside of the turn known as adverse yaw. When you enter a turn, you should depress the rudder in the same direction of the turn to help compensate for adverse yaw. Once you are established in the turn, you may neutralize the ailerons to prevent further roll. Since the cause of adverse yaw is removed, rudder pressure also can be relaxed. When you roll out of the turn, you should apply coordinated aileron and rudder pressure in the opposite direction of the turn to return to a wings level attitude. During a turn, the outside wing travels faster than the inside wing and creates more lift, which may cause the airplane to continue rolling beyond the desired bank angle. You can correct this overbanking tendency by applying a small amount of aileron in the opposite direction of the turn. Two terms which are used to define the performance of an airplane in turning flight are rate of turn and radius of turn. Rate of turn is the amount of time for an airplane to turn a specified number of degrees. Every aircraft will turn at the same rate when flown at the same airspeed and angle of bank. If airspeed is increased and the angle of bank remains the same, the rate of turn will decrease. Conversely, A constant airspeed with an increased angle of bank will result in a faster rate of turn. The radius of turn, or the distance an aircraft must be flown to complete a turn, is also dependent on airspeed and angle of bank. For example, when airspeed is increased and the angle of bank remains the same, the radius of turn increases. However, if the airspeed remains the same and angle of bank is increased, the radius of turn is smaller. Load factor is the ratio of the load supported by the wings to the actual weight of the airplane. An airplane in straight and level unaccelerated flight has a load factor of 1, which means the wings are supporting only the actual weight of the airplane and its contents. You may be more familiar with the term G-force, which is used to describe loads imposed on a maneuvering aircraft. You can relate G-force to the feeling you get while riding a roller coaster. As you enter a bank turn on a roller coaster, you feel the forces created by the combination of centripetal force and inertia as seat pressure. The pressure you feel is, in reality, an increase in load factor that is expressed in G's. As the roller coaster reaches the top of the track and begins a rapid descent, you may feel a sensation of weightlessness if centripetal force and inertia cancel each other out. It's important to note that a change in load factor can occur at any time due to pilot control input or environmental conditions, such as turbulence. The amount of stress which an airplane can withstand before structural damage or failure occurs is called the limit load factor. Most general aviation aircraft are certificated in one of 3 categories: normal, utility, or acrobatic. Many general aviation airplanes are certificated in the normal category, with a limit load factor of 3.8 positive Gs and 1.52 negative Gs, which is sufficient for basic training maneuvers. Airplanes which are certificated in the utility category have a limit load factor of 4.4 positive Gs and 1.76 negative Gs. Acrobatic airplanes are even less restricted, with a limit load factor of 6 positive Gs and 3 negative Gs. Regardless of the category, it's very important to adhere to proper loading techniques and always fly within the limits listed in the pilot's operating handbook. Another way to avoid possible damage to your airplane by excess loads is to observe the design maneuvering airspeed, or VA. Related to stall speed, this is the maximum speed at which you can use full or abrupt control movements without overstressing the airframe. VA is normally not marked on the airspeed indicator, since it varies with total weight. Maneuvering speed decreases with a decrease in weight because an airplane operating at a lighter weight is subject to more rapid acceleration from gusts and turbulence. If G loading increases while operating below maneuvering speed, your airplane will stall before the limit load factor is exceeded, thus avoiding potential damage to the airplane. Understanding the forces acting on your airplane will improve your ability to perform more complex maneuvers with greater accuracy and safety as you progress through your flight training.
In the early 1900s, airplanes were just beginning to take to the skies. Back then, there were relatively few airplanes and more than enough airspace to hold them all. However, as time passed, the number of aircraft sharing the same airspace grew. Today, air travel is commonplace. Airplanes have become bigger, sleeker, and faster. Over the years, the number and types of aircraft changed, but some basic things have remained the same. Now, more than ever, you as a pilot must abide by the rule of see and avoid to prevent a mid-air collision. The introduction of air traffic control, or ATC, and radar has helped to alleviate some of the congestion problems. But it is still the sole responsibility of each pilot to see and avoid. Although this may seem simple enough, learning to spot and avoid other aircraft isn't always easy. For example, there are 5 F-4 jet fighters in this picture. Can you spot them? As you progress in flying, your eyes will eventually become trained to pick out other air traffic. In fact, you should spend about 70% of your piloting time looking for other aircraft. This technique, called scanning, involves dividing your viewing into segmented areas of about 10 degrees each. Focusing on each section for about 1 second allows you to keep your eyes moving, yet still enables you to easily pick out traffic. If something does catch your attention, you should identify the object before moving on to the next section. Be sure to include the entire visual area in your scan, since conflicting traffic can come from any direction. However, blind spots caused by the design of the airplane can block part of your field of vision. These blind spots will vary from one aircraft to another, depending on the location of the wings and the cockpit. For example, in a high-wing aircraft, the area directly under the airplane is blocked by the fuselage, while the wings make it difficult to see the area above the airplane. When you make a turn in a high-wing airplane, your vision is blocked in the direction you are turning. Before starting a turn, you should raise the wings slightly to clear the area. Then make the turn. In a low-wing aircraft, the fuselage blocks your view under the airplane, as well as some of the area above and behind. The view downward is further restricted by the wings. When you make a turn in a low-wing aircraft, the view in the direction away from the turn is blocked. Therefore, before making any turns, whether you're in a high-wing or a low-wing airplane, you should always scan the entire area for possible traffic. This is especially true when you're near an airport. Also, during prolonged climbs in a high-wing or prolonged descents in a low-wing airplane, you should make shallow S-turns to increase your field of vision. As you're learning to fly, your instructor will have you do clearing turns before you begin any flight maneuver. These turns involve at least a 180-degree change in direction. The most common way to clear an area is to make 2 turns in opposite directions, each one being 90 degrees. If you do spot another aircraft, its relative position will help you determine if it presents a potential hazard to you. If the other plane appears to be at or near the horizon, then it's near your altitude. Even if the traffic isn't near the horizon, you should always keep it in sight until it has passed by, since the other pilot may decide to change altitudes. When an aircraft is on a collision course with you, its position in the windshield will barely move as it approaches. Because the plane doesn't appear to be moving, it probably won't catch your eye as easily. For this reason, it's important that you develop and use the proper scanning technique at all times. When you do find yourself near another aircraft, there are certain regulations which determine who has the right-of-way. These regulations not only determine the right-of-way for converging airplanes, but also state what types of aircraft have priority. For instance, balloons, gliders, airplanes towing gliders, and airships all have right-of-way over other powered aircraft. Any plane in a state of emergency has the right-of-way over all other aircraft. When 2 airplanes are approaching head-on, both should yield to the right. When you're overtaking another airplane, the plane in front has the right-of-way. In this case, you should alter your course and overtake the aircraft well to the right. If an airplane is converging on you from the right, it has the right-of-way. Just like 2 cars meeting at an intersection, you must yield to the vehicle on the right and change your course to pass behind the other aircraft. During airport operations, aircraft in the process of landing have the right-of-way over aircraft on the ground, as well as others in the vicinity. If 2 aircraft are approaching to land, the one at the lowest altitude is given right-of-way. The biggest problem with the see and avoid concept is that if your aircraft isn't seen by other pilots, they won't be able to avoid you, even though you may have the right of way. You can help other pilots spot you on the ground by turning your landing lights on when you're taxiing on, across, or holding in position on any runway. In the air, turn on your landing lights when you're in the vicinity of an airport, both during the day and at night. In addition, your anti-collision lights should be on whenever the engine is running, except at times when their brightness could compromise safety. To further reduce the chance of mid-air accidents, cruising altitudes were established to keep sectors of traffic flowing in one direction, away from traffic moving in the opposite direction. These cruising altitudes apply to pilots flying under visual flight rules, as well as those under instrument flying rules. Visual flight rules, or VFR, means flying and navigating primarily with the use of outside visual references. When weather conditions restrict outside vision, VFR flight is often not possible. IFR, or instrument flight rules, apply to specially trained pilots who hold instrument ratings and are flying aircraft equipped for instrument flight. The cruising altitudes start at 3,000 feet above the ground. VFR aircraft flying eastbound on magnetic courses between 360 degrees and 179 degrees would fly at odd 1,000 feet plus 500. Westbound aircraft fly at even 1,000 feet plus 500. IFR traffic flies at odd or even 1,000 feet depending on the direction of travel. There are also minimum safe altitudes you must adhere to in order to ensure that you have enough time to take the proper corrective action in the event of an emergency. When you're flying over uncongested areas, you must fly at least 500 feet above the surface. Over open water or sparsely populated areas, there is no minimum altitude. The only restriction here is that you cannot fly closer than 500 feet to any person, vessel, vehicle, or structure. However, regulations do say that you must always operate at an altitude which would allow you to make an emergency landing without causing undue hazard to persons or property on the ground. A larger safety margin is needed over congested areas such as towns or cities. Regulations require that you fly at least 1,000 feet higher than the top of the highest obstacle when you're within 2,000 feet of it. Large metropolitan areas pose a more serious problem because they have fewer emergency landing areas. By flying at higher altitudes than those required by regulation, you might be able to buy the extra time needed to tend to any problem which might occur. In addition, a higher altitude increases your glide distance, giving you a larger selection of emergency landing spots. Another important aspect of safety is avoiding areas protected for national security reasons. An inadvertent entry into such an area can result in your aircraft being intercepted. Careful pre-flight planning and vigilance in flight can help avoid most problems. In addition, studying the federal regulations and interception procedures outlined in the AIM prior to departure can help eliminate confusion and a potentially dangerous situation in flight. For example, an aircraft that is in front of you that is rocking its wings is indicating your flight has been intercepted. You must follow the intercepting aircraft. As the skies become more crowded, the skills of detecting other aircraft and avoiding potential hazards becomes increasingly important. Using these skills will help ensure enjoyable flying in the years to come.
By the time you've finished your training, the airport will feel like your second home. Depending on where you train, this might be a small grass strip, a large complex in a big metropolitan area, or one of the thousands of airports in between. It could be an airport without an operating tower, where you are responsible for determining the active runway and following local procedures. Or it could be at a controlled airport. When a control tower is operational, air traffic controllers will instruct you to follow certain procedures depending on whether you're in the air or on the ground. To operate at a controlled airport, you must have two-way radio contact with ATC. Airports are the hub of all air operations. Not only is this where aircraft of various types take off and land, but this is also the place where aircraft are parked or hangared, and where you can rent, buy, or service aircraft. The larger airports can have several hundred operations per day. The logistics of moving this many aircraft over and around each other requires precise instructions and procedures. To relieve some of the problems associated with having so many aircraft operating in a concentrated area, the FAA has established some standards and procedures to help pilots better orient themselves around an airport. One example of this standardization is airport signs. There are 6 types of airport signs which provide you with information while taxiing. These signs are mandatory instruction, location, direction, destination, information, and runway distance remaining. First, mandatory instruction signs are used to denote an entrance to a runway or critical area, and to areas where aircraft are prohibited from entering. These signs have white lettering on a red background and usually indicate the holding position for these areas. There are 2 different types of location signs. The ones used to identify either a runway or taxiway have yellow lettering and a yellow border on a black background. Runway boundary and instrument landing system critical area boundary signs have black markings on a yellow background. Direction signs have the same black on yellow markings and contain arrows, which indicate the direction of taxiways leading from an intersection. Destination signs indicate the general direction to remote locations such as runways, terminals, military areas, civil aviation areas, and fixed base operators. Signs advising you of nice-to-know items are referred to as information signs. The runway distance remaining signs provide valuable information during takeoff or landing. These signs have a white number on a black background and are located along the side of the runway. The number indicates the distance remaining in thousands of feet. Now let's look at another example of standardization: runway markings. The basic VFR markings found on a hard-surfaced runway consist of white runway numbers and a center line. At each end of a runway is a set of numbers, painted so they appear upright to an approaching aircraft. These numbers represent the approximate magnetic direction of the runway, rounded to the nearest 10 degrees, with the last 0 omitted. In other words, if you were landing in a no crosswind condition on runway 29, your magnetic heading would be approximately 290 degrees during final approach. When landing on the same runway, but from the opposite direction, your final approach heading would be 110 degrees magnetic. This numbering of the runway to correspond to its magnetic direction can help you determine the runway's orientation long before you actually see the numbers. When 2 runways are built parallel to each other, both will carry the same numerical designation. However, the left runway number will have an L, while the right runway will have an R. Where 3 parallel runways exist, the letter C is added to the center runway designation. In addition to the center line, some runways used for IFR operations have additional markings, such as threshold markers, which consist of 2 sets of 4 parallel bars. Some runways have displaced thresholds, meaning the end of the runway is not suitable for landing. This usually is because of obstructions near the approach end, or the marked portion of the runway is not strong enough for repeated landings. You can identify these portions of the runway by arrows painted down the center, pointing toward a large white line that represents the actual runway threshold. You cannot land in a displaced threshold area, but it can be used for taxiing, takeoff, and landing rollout. Stopways or blast pads are marked with a chevron pattern. These areas are not to be used for landing, takeoff, and taxiing. All taxiway markings are in yellow and provide guidance between the parking areas and the runway. A broad yellow dashed line painted across a taxiway indicates a hold position at intersecting taxiways. Runway holding position markings consist of 4 yellow lines, 2 solid and 2 dashed. The solid lines are always on the side where the aircraft is to hold. These holding lines may also be used on runways that intersect another runway. At airports with an operating control tower, a clearance is required before crossing these lines onto an active runway. If you receive a hold short instruction, you must repeat that instruction back to the tower or ground controller. Any runway or taxiway that is marked with an X on each end is closed to all operations. During periods of limited visibility or at night, many airports are lighted to make operations safer. The amount of lighting varies greatly, depending on the size of the airport. Taxiways are outlined in blue lights or blue reflectors. Additional taxiway lighting may be used during periods of low visibility. For example, green taxiway centerline lights may be available at some airports. Yellow in-pavement clearance bar lights indicate the location of holding points at intersecting taxiways. They are designed to increase awareness of holding positions during periods of low visibility. Runway guard lights are elevated or in-pavement yellow flashing lights installed at runway holding positions. They indicate where a taxiway intersects a runway. Stop bar lights consist of a row of red in-pavement lights. They are designed to confirm an ATC clearance to enter or cross an active runway during periods of low visibility. Pilots should never cross an illuminated red stop bar. Runways are outlined by white lights. On runways used for instrument approaches, yellow lights are used as a visual caution zone on either the last 2,000 feet or half the runway length, whichever is less. Some larger airports have flush-mounted centerline lights as well. To mark the end of the runway, the portion of centerline lights between the last 3,000 and 1,000 feet are alternating red and white. The last 1,000 feet of lights are red. To mark the beginning of a runway, green lights are placed at the threshold. These same lights, when viewed from the opposite direction, will be red, indicating the end of the runway. Sometimes, white strobe lights accompany the threshold lights. Sequenced flashing lights can be seen on some instrument runways in the approach area along the extended centerline. These lights can vary in intensity and are used to guide aircraft to the runway during instrument approaches. At some airports, you can turn the runway lights on or adjust their intensity by keying the microphone a specific number of times within a certain time period. At monitored or controlled airports, you can also have the approach and landing lights adjusted by asking the tower or flight service station to temporarily adjust the lighting for you. Another light you may see is the airport beacon. This beacon aids pilots in identifying the airport from several miles away and is operational from sunset to sunrise and in some cases during periods of IFR conditions. Civil airports for land planes display an alternating green and white flashing beacon. Beacons at military fields emit 2 white flashes alternating with a green flash. Lights located on obstructions, such as towers and tall buildings, can either be red or white and sometimes may be flashing. These lights assist you in picking out obstacles that could be high enough to present a hazard. At some airports, visual glide slope indicators are installed to help pilots judge the proper descent to the runway. One type of system is the Visual Approach Slope Indicator Lights, or VASI. This system contains two separate bars of lights, which normally represent a 3-degree glide slope. When you're above the glide path, both indicators will be white. When you're below the 3-degree glide path, both will be red. When the lower or near bar of lights is indicating white and the second far bar is indicating red, your airplane is on the VASI glide path. Another type of glide slope information system is PAPI, or Precision Approach Path Indicator. Instead of comparing two bars of lights as with the VASI system, you compare lights on the same bar. When you're above the glide path, all 4 lights will indicate white. As your aircraft descends and nears the glide path, the lights on the right will begin to turn red. As the aircraft intercepts the proper glide path, the 2 indicators on the right will show red, while the 2 on the left remain white. When 3 or more lights show red, you are beneath the glide path and are too low. Another common aid at airports is a wind indicator. Since wind is an important factor in determining takeoff and landing performance, airports use 1 or more basic wind indicators. The most common type of wind indicator is the windsock, which consists of a tube with one end bigger than the other. Wind blowing through the larger end causes the smaller end to streamline downwind. A more elaborate type of wind indicator is the wind T, which will weather vane into the wind. It represents an airplane pointed in the direction of takeoff or landing. When a wind T is co-located with another wind indicator, it may be manually aligned with the runway to indicate the direction of landing. Another landing direction indicator is the tetrahedron. Like the wind T, it may swing freely in the wind or may be manually positioned. When determining the landing direction using a tetrahedron, remember the small end points into the wind. Also, if the wind is calm, the tetrahedron may not be aligned with a designated calm wind runway. In this situation, use extreme caution. When installed at uncontrolled airports, the wind and landing direction indicators are usually placed in the middle of a segmented circle. The segmented circle helps identify the location of the wind direction indicator, and the extensions indicate the correct traffic pattern for each runway at the airport. Each year, hundreds of aircraft are destroyed or damaged by collisions with other aircraft or vehicles on the ground. The majority of these accidents are preventable. All pilots must be more vigilant and become aware of the dangers of runway incursions. Ground operations during low visibility and bad weather can challenge situational awareness. When operating at an airport, always be aware of other aircraft and vehicles moving around you. Also, be aware of situations that increase the likelihood of an incursion. A runway incursion can involve an aircraft, vehicle, person, or object on the ground that creates a collision hazard. A misunderstood clearance can also result in a runway incursion or a potential collision. There are several procedures that you can follow and precautions that you can take to avoid a runway incursion. Complete as many checklist items as possible before taxiing. Concentrate on your primary responsibilities. Do not become absorbed in other tasks or conversation while the aircraft is moving.
Cessna 62740, hold short runway 17 right, landing traffic.
Cessna 740, holding short runway 17 right for landing traffic.
Read back all clearances involving active runway crossing, hold short, and taxi into position and hold instructions. If you are unsure of your position, ask for assistance. Controlled airports can offer progressive taxi instructions.
Cessna 53549er requests progressive taxi instructions.
Cessna 549er, proceed to the general aviation ramp via Alpha. Caution, construction on ramp near right.
Report deteriorating or confusing airport markings, signs, and lighting to the airport operator or FAA officials. Also report confusing or erroneous airport diagrams and instructions. At busier airports, where there is an increased amount of aircraft, air traffic controllers must make use of the existing airport surface to keep traffic flowing at a maximum efficiency level. Land and hold short operations, also known as LAHASO, are used to help air traffic controllers work with more aircraft at one time, allowing a more efficient use of the runway environment.
Warrior 83312, you are cleared to land. Runway 26, hold short of runway 35.
Specific knowledge-based training must be completed before any pilot can conduct LAHASO. In addition, student pilots conducting solo operations are not authorized to participate in land and hold short operations. The regulations state that pilots shall become familiar with all available information concerning their flight, including runway lengths and takeoff and landing distance for the conditions at the airport of intended use.
Warrior 312, cleared to land runway 26, hold short runway 35.
Acceptance of land and hold short instructions indicates that you fully understand the clearance, including all related procedures.
Cessna 52241, cleared to land runway 35. Hold short Bravo intersection for crossing traffic.
Cessna 241, unable to hold short at Bravo.
The pilot in command has the final authority to accept or decline any land and hold short clearance. The safety and operation of the aircraft remain the responsibility of the pilot. As we have seen, airports play an important role in aviation. In this section, we covered the major items of interest to a VFR pilot. However, each airport has its own unique characteristics. Further sections will introduce you to publications which you can use to better acquaint yourself with unfamiliar airports.
When traveling to a new area in your car, road signs and road maps help you get to your destination. In the same manner, aeronautical charts guide you in the air when you leave your local area. The charts you'll be using for navigation represent the Earth's surface, and throughout your training and flying career, you will be required to locate and identify certain positions on the chart. You can do this by using lines of latitude, which are parallel to the Earth's equator, and lines of longitude, which run from the North Pole to the South Pole. Using the equator as a starting point, we can plot lines of latitude north and south from 0 degrees at the equator to 90 degrees at the poles. By international agreement, the starting point, or 0 degrees longitude, runs through Greenwich, England. The 0 degree line is called the prime meridian. All other lines of longitude are plotted in degrees east and west through 180 degrees. Each degree of latitude is divided into 60 equal segments called minutes, and each tick mark represents 1 minute. Degrees of longitude are also marked in the same way. By using these degrees and minutes, you can identify a position anywhere on the chart. For example, if you were located at the Mentone Airport, you could determine its coordinates by first locating the nearest latitude line, which is 41 degrees. Then count the number of minutes up from 41. In this case, it is 9 minutes. Since latitude increases as you go north in the northern hemisphere, you must add the 9 minutes to 41 degrees. You can also do the same for longitude. Since longitude increases as you go west in the United States, you must add about 4 minutes to 86 degrees. Your geographic coordinates are 41 degrees 9 minutes north latitude and 86 degrees 4 minutes west longitude. Notice that the latitude is always given first when stating coordinates. In addition, you can use minutes of latitude to measure distance. Each minute is equal to 1 nautical mile. For example, to measure the distance between Mentone Airport and Fulton County Airport at Rochester, you can use the latitude lines. The distance is 8 nautical miles. You can verify this by using the nautical mile scale on the chart. Make sure you don't measure distances using minutes of longitude, because those distances will vary depending upon their position with respect to the poles. There are many problems associated with trying to portray a spherical object, such as the Earth, in chart form. When we try to flatten any spherical object, distortions occur. Over the years, several charting techniques called projections have been developed to minimize these distortions and inaccuracies. One method is the Lambert conformal conic projection, which makes a sectional cut through the globe. This projection is used for the 3 charts you will use most during your VFR flying. These include the World Aeronautical Chart, the Sectional Chart, and the VFR Terminal Area Chart. Since the scale on a World Aeronautical Chart, or WAC chart, is 1 to 1 million, it covers the most area. A 1 to 1 million scale means that each inch on the chart represents 1 million inches, or approximately 14 nautical miles on the actual surface. The sectional chart is the most widely used chart. It gives you more detail than the WAC chart, since its scale is 1 to 500,000. Therefore, 1 inch on the chart represents about 7 nautical miles. A VFR terminal area chart provides the most detail. Its scale is 1 to 250,000 and covers a selected terminal area. It provides you with a detailed portrayal of the area surrounding a major airport. Since all 3 of these VFR charts provide basically the same information, you can become familiar with them by studying just one. In this case, we'll use a sectional chart. The front panel of each sectional has a chart index, and the shaded block depicts the area that is covered by the chart. Sectionals are named for the major city that lies within the coverage area. For example, this is the Albuquerque sectional. Sectional charts show the locations where terminal area charts can be found by outlining the region with a magenta square. Below the U.S. chart index, you can find information on chart elevation. The color bar gives you a graphic description of elevation changes. The highest terrain elevation on the sectional is printed at the top of the color bar, as well as to the left. Its geographic coordinates are also given. Within each area enclosed by lines of latitude and longitude is a distinct number showing the maximum elevation figure, or MEF, in thousands and hundreds of feet. In this case, the 60 represents 6,000 feet. The MEF is the highest known feature in each quadrangle, including terrain and obstructions. An explanation of the MEF is usually found on or near the front panel. General terrain elevation above sea level can be determined by referring to the contour lines on the chart. These lines connect points of equal terrain elevation. This model shows the relationship between the terrain shape and the contour lines shown on the chart. From a side view, you can see that the lines parallel the base at regular intervals. From a higher angle, notice that the lines follow the irregularities of the slopes, valleys, and cuts of the mountains. A top view of the lines is representative of what you will see on the chart. Intervals between contour lines for a particular chart are shown on the front panel. Now let's look at how to interpret the information on the chart. As you unfold the map, you will notice the legend on the back panel. At the top of each panel are the words north and south, indicating the chart coverage area is divided into north and south regions, with each one displayed on a different side. Now we'll examine some of the more common symbols found on the chart legend. Of primary importance are the airport symbols. A blue symbol indicates an airport with a control tower, while a magenta-colored symbol shows an airport without a tower. Airport symbols are shown in a variety of shapes. Runway diagrams shown inside a colored circle indicate the runways are hard-surfaced and range in length from 1,500 to 8,069 feet. When an airport diagram is not in a colored circle, it indicates that at least one of the hard-surfaced runways is longer than 8,069 feet. Near the airport diagram, you will find the name of the airport and information about its facilities. This is the University of Illinois Willard Airport. The abbreviation after the airport name is its three-letter identifier. CT indicates there is a control tower at the field, and it has a primary frequency of 120.4. The star means that the tower does not operate continuously. The C symbol in the filled-in circle indicates that you should use the tower frequency as the Common Traffic Advisory Frequency, or CTAF, when the tower is not operating. The C symbol is also used to show the CTAF at the airport without a tower. In this example, the CTAF is the Unicom frequency. The RP27 symbol is used to specify a right-hand traffic pattern for runway 27. ATIS, or ATIS, stands for Automatic Terminal Information Service, which is broadcast on a VHF frequency of 124.85. This pre-recorded message will give you vital information on airport conditions. 754 is the elevation of the airport in feet. The L indicates runway lighting, and the star tells you that lighting limitations exist. In this case, you should refer to the airport facility directory for more information. The next number, 81, is the length of the longest runway in hundreds of feet. Here, the longest runway is 8,100 feet. However, the usable length may be less. 122.95 is the Unicom frequency. At airports where a flight service station is located on the field, the letters FSS are included above the airport name. Another vital block of information you will be interested in is the navigational aid. The nav aid box contains the name of the facility, frequencies, and the Morse code identifier. The flight service station providing voice communication is sometimes identified below the box. In this case, it's the Roswell FSS. Notice that the VHF radio frequencies are colored blue, while low and medium frequency nav aids are shown in magenta. An underline means that there is no voice communication available on this frequency. A circled H, T, or A in the upper right-hand corner of the information box indicates that specific weather information is available from this nav aid. The H in this case means HIWAS is available. Additional information found on the chart concerns obstructions. Let's take a look at some of the common symbols. One is for obstacles less than 1,000 feet AGL. And another symbol is for obstacles 1,000 feet AGL and above. Printed next to the symbol is the height of the structure above sea level. In parentheses is its height above the ground. If the structure has high-intensity lighting, the lighting symbol is included. In addition to towers, which can be identified on the chart, roads and highways make good landmarks for navigation. They are indicated by solid gray lines. Divided highways are shown by double lines. Primary and secondary roads are illustrated by single gray lines. The lines for primary roads are slightly thicker than those for secondary roads. Railroad tracks also make excellent visual aids. Another good reference to use while flying is an industrial plant. Large stacks sometimes produce smoke or steam, which is easily visible from the air. You can often spot the smoke many miles before you actually see the plant. Cities make good checkpoints. Cities and larger towns are shown on sectionals in yellow, which defines the built-up area. Smaller towns, on the other hand, are only represented by a circle on the map. Since you can't identify the towns by their shape, you must use other landmarks to prevent mistaking similar-looking towns, especially those close to each other. Besides highways and railroad tracks, some of these landmarks are racetracks, outdoor theaters, and bridges. Terrain features can also help you identify your location. Reservoirs and lakes are shown by an outline representing the approximate layout of the body of water. A blue line on a chart represents a river. The wider the line, the wider the river. Up to now, you have seen the more identifiable features on the sectional chart. But your chart also has certain airspace information, which you can interpret only by careful study. As you learned earlier, all airspace is divided into two main classifications: uncontrolled and controlled. Uncontrolled, or Class G airspace, usually begins at the Earth's surface and extends upward to the base of the overlying controlled airspace. Class E controlled airspace is identified by tinted bands with the color dissolving into the area of controlled airspace. The height of the floor of this airspace is identified by different colors. A blue tinted band indicates the floor begins at 1,200 feet above the surface. A magenta tinted band indicates the floor starts at 700 feet above the surface. In some areas, the floor of Class E airspace may begin at altitudes other than 700 or 1,200 feet above the ground. These areas are indicated by overlapping blue lines. The floor of Class E airspace is depicted next to the line. In this example, the floor begins at 5,300 feet MSL. At some airports, dashed magenta lines indicate that Class E airspace begins at the surface. Another type of Class E airspace is a federal airway, commonly referred to as a Victor airway. The center line of an airway is marked in blue on sectional charts. Several other types of controlled airspace are also depicted on sectional charts. These include Class D airspace with its lateral limits appearing as blue dashed lines and its vertical limit indicated in hundreds of feet. If Class C airspace is designated at an airport, it will be shown like this. The solid magenta lines indicate the lateral limits of both the inner and outer circles. The extent of the outer area is not depicted on sectional charts. Class C vertical limits are shown in hundreds of feet MSL. The upper limit is printed over the lower limit or floor of the airspace. In this example, Wichita's outer circle has an upper limit of 5,300 feet MSL and a floor of 2,700 feet. The inner circle has the same upper limit, but the floor extends down to the surface. Class B airspace is outlined by solid blue lines, with the upper and lower altitude limits depicted within each sector. Class B airspace is also shown on VFR terminal area charts. The area covered is indicated on sectional charts by a wide blue line. If fixed-wing special VFR operations are prohibited, the term No SVFR will be included directly above the primary airport's information block. Other types of airspace you will find displayed on the chart are prohibited areas, restricted areas, military operations areas, and warning areas. In this discussion, we've talked about the major features of aeronautical charts. To get additional information, you will need to review the manual and the chart legend. Aeronautical charts are the basis for all air navigation. The time spent becoming familiar with them will be well worth your effort. The ability to quickly find chart information reduces your workload in the air, allowing you more time to devote to your flying.
Your airplane gives you the freedom to fly almost anywhere you want to go. With this freedom comes responsibility. The responsibility to know the requirements of the area in which you're operating and to ensure that you and your aircraft are properly equipped and certified to fly in that airspace. The sky over the United States is divided into various airspace categories. The two main categories are controlled and uncontrolled. Special use airspace and other airspace areas are additional categories. First, let's take a look at controlled and uncontrolled airspace. In controlled airspace, all aircraft operators are subject to certain pilot qualifications, equipment requirements, and operating rules which are specified in the regulations. In addition, you may be required to be in contact with Air Traffic Control, or ATC, while flying in controlled airspace. ATC may provide you with services such as traffic advisories, sequencing of aircraft, and radar separation. Radar services are improved by use of a transponder, which is an electronic device aboard the airplane that enhances your aircraft's identity on an ATC radar screen. If your aircraft is equipped with a transponder, regulations require you to use it whenever you fly in controlled airspace. You are also required to have a transponder with Mode C altitude encoding capability anytime you are flying at or above 10,000 feet mean sea level. This, however, excludes the airspace at and below 2,500 feet above ground level. The use of this equipment will be discussed in a later program. Controlled and uncontrolled airspace is classified using alphabetical designations based on the standards set forth by the International Civil Aviation Organization, commonly referred to as ICAO. Controlled airspace consists of those areas designated as Class A, B, C, D, and E airspace. Uncontrolled airspace is designated as Class G. Currently, there isn't any airspace in the U.S. meeting the ICAO definition for Class F. The classification of airspace is relative to the complexity of the operational requirements placed on the pilot and aircraft. With this in mind, let's take a look at Class A airspace. Class A airspace extends from 18,000 feet MSL up to and including 60,000 feet MSL. To fly in Class A airspace, you must hold an instrument rating, operate under an IFR flight plan, and be controlled directly by ATC. Now let's discuss the classes of airspace that you'll become familiar with while flying under visual flight rules. VFR sectional charts can be used to identify the various classes of airspace you will be flying in. The specific dimensions of most of the airspace classes are depicted on these charts. Class B airspace surrounds our nation's busiest airports. In Class B airspace, radar services are provided by ATC to separate all arriving and departing traffic. Although the shape of Class B airspace may vary to meet the specific needs of each location, the general design is a series of expanding layers. This shape allows arriving and departing airplanes to remain in controlled airspace as they travel between the airport and en route portion of the flight. To operate within Class B airspace, there are specific requirements that must be met. Prior to entering the airspace, you must get an authorization or clearance from ATC. This means your aircraft must be equipped with a two-way radio so you can communicate with ATC. In addition, your aircraft must have a transponder with Mode C altitude encoding capability. The transponder requirement extends out to 30 nautical miles from the primary airport and covers the airspace from the surface up to 10,000 feet MSL. To operate within Class B airspace, you must hold at least a private pilot certificate. There is, however, one exception to this regulation. Student pilots may operate within Class B airspace if they first comply with the training requirements listed in the regulations and have the appropriate instructor endorsement. Keep in mind that some Class B primary airports are so congested that takeoffs and landings by student pilots are prohibited. These airports are listed in FAR Part 91 and in the AIM. Class C airspace exists at designated airports where the volume of traffic is not as great as in Class B airspace. But ATC does provide radar services to all aircraft. This airspace usually consists of a core area or inner circle extending out 5 nautical miles from the primary airport, and a shelf area or outer circle with a 10-mile radius. The core area begins at the surface, while the shelf area starts at 1,200 feet AGL. Both have an upper limit of 4,000 feet above the airport elevation. Prior to entering Class C airspace, you must establish two-way communications with ATC and maintain radio contact while in the airspace. Your aircraft must also be equipped with an operable transponder with Mode C capability. This requirement extends up to 10,000 feet MSL. An outer area exists out to 20 nautical miles from the primary airport in association with Class C airspace. Although two-way radio communications are not required, inbound VFR pilots are strongly encouraged to contact ATC when flying in the 20-mile outer area. ATC normally provides radar services in this area to improve safety and aircraft separation. Another classification you need to know is Class D airspace. Class D airspace is located around airports that have operating control towers. The control tower provides air traffic control and weather reporting services to arriving and departing aircraft in the terminal area. The lateral dimensions of Class D airspace are normally based on the instrument approach procedures at the airport. Since this airspace often contains arrival extensions, the lateral limits vary from airport to airport. Normally, the ceiling of Class D airspace is 2,500 feet above the airport elevation. The ceiling may vary, though, due to requirements unique to each airport. Prior to entering Class D airspace, you must establish and maintain two-way radio communications with the control tower. At airports where the control tower is only operational at certain times, the airspace will be designated as Class D only when the tower is open. When the tower is not in operation, this area is referred to as Class E airspace. If there is no observer on the field to provide weather reporting service, the airspace will be designated as Class G. Two-way radio communications with ATC are not required in either Class E or Class G airspace for VFR flights. However, in those Class E and Class G airspace areas which have an operating control tower, you must communicate with the tower when you are within 4 nautical miles and at or below 2,500 feet AGL. There are also some airports where the instrument arrival extension does not require establishing radio contact with the control tower. In this case, the extension area is designated as Class E airspace. The Class E designation also covers the remaining controlled airspace and consists of several different segments. ATC services are provided to IFR traffic in Class E, and some services are available on request for VFR flights. One segment of Class E airspace is found around non-towered airports which have approved instrument approach procedures. The purpose of this area is to allow IFR traffic to remain in controlled airspace while transitioning from the en route environment to the airport. The base of this type of Class E airspace begins either at the surface or at 700 feet AGL. The lateral limits may vary and are depicted on sectional charts. In both cases, the vertical limit extends upward to the base of the overlying airspace. At airports where Class E airspace begins at the surface, weather reporting services are provided by an FAA-designated weather observer. At certain times, this service may not be available, and the airspace will then be designated as Class G. Away from airports, much of the Class E airspace begins at 1,200 feet AGL, and most of your flights will be conducted in this airspace. Federal Airways, also known as Victor Airways, are designated as Class E airspace. These airways allow you to fly from one location to another by radio navigation. These airways are normally 8 nautical miles wide and begin at 1,200 feet AGL. The low-altitude airway system includes the airspace up to, but not including, 18,000 feet MSL. Unless designated at a lower altitude, Class E airspace also covers the 48 contiguous states, the District of Columbia, and a portion of Alaska, beginning at 14,500 feet MSL and ending at the base of Class A airspace. It does not, however, include the airspace within 1,500 feet of the surface. The last letter designation for U.S. airspace is Class G, or uncontrolled airspace. Essentially, all airspace not designated as Class A, B, C, D, or E is uncontrolled. ATC doesn't have any responsibility or authority for aircraft operations in Class G airspace, and unless the area contains an operating control tower, there are no two-way radio communications or special equipment requirements. Although some segments of airspace we have discussed do not require communication or special equipment, it is still important to know their dimensions because of required weather minimums. Specific cloud clearance and visibility minimums have been established for VFR flights in both controlled and uncontrolled airspace classes. Let's take a look at controlled airspace weather minimums first. To operate VFR in Class B airspace, you must remain clear of clouds and maintain at least 3 statute miles flight visibility. You must also maintain 3 statute miles visibility in Class C and D airspace, but the cloud clearance increases to 500 feet below, 1,000 feet above, and 2,000 feet horizontally. These same minimums apply in Class E airspace below 10,000 feet MSL. In Class E airspace above 10,000 feet MSL, though, the minimums increase. You must maintain 5 statute miles flight visibility and maintain a distance from clouds of 1,000 feet below, 1,000 feet above, and 1 statute mile horizontally. Besides the basic VFR weather minimums, there are additional limitations when operating in the vicinity of an airport in controlled airspace. For example, to operate VFR beneath a ceiling within the lateral boundaries of controlled airspace, which extends to the surface, the ceiling must be at least 1,000 feet. In addition, within the lateral boundaries of the surface areas of Class B, C, D, and E airspace, VFR pilots cannot land, take off, or enter an airport's traffic pattern unless the visibility is 3 statute miles or better. These requirements give VFR and IFR pilots the necessary visibility to see and avoid each other during approaches and departures. When the weather is below these VFR minimums, you may be able to obtain a special VFR clearance from ATC. This type of clearance allows you to take off and land as long as you have 1 mile visibility and can remain clear of clouds. Keep in mind, a special VFR clearance cannot be issued at night unless you have a current instrument rating and your airplane is equipped for instrument flight. In addition, special VFR clearances are not issued to fixed-wing aircraft during the day or night at some of the nation's busier airports. A listing of these airports can be found in FAR Part 91. The lowest weather minimums occur in Class G, uncontrolled airspace, during the day. When flying at or below 1,200 feet AGL, regardless of your MSL altitude, you must maintain a flight visibility of 1 statute mile and remain clear of clouds. During the day, when flying higher than 1,200 feet AGL, but less than 10,000 feet MSL in Class G airspace, the flight visibility remains at 1 statute mile. The cloud clearance increases, though, to 500 feet below, 1,000 feet above, and 2,000 feet horizontally. At night, in Class G airspace, the same cloud clearance minimums apply, but the visibility increases to 3 statute miles below 10,000 feet MSL. These same minimums also apply to any airspace above 10,000 feet, that is within 1,200 feet AGL. There is one exception to these weather minimums in Class G airspace. You may operate an airplane in the traffic pattern at night with a minimum visibility of 1 statute mile. However, you must remain clear of clouds and stay within 1/2 mile of the runway. Finally, if you are operating more than 1,200 feet AGL and you are at or above 10,000 feet MSL in Class G airspace, your weather minimums increase. Here, you are required to maintain 5 statute miles flight visibility and remain 1,000 feet below, 1,000 feet above, and 1 statute mile horizontally from clouds. Airspeed restrictions have also been established for operations in both controlled and uncontrolled airspace. Unless otherwise authorized, you cannot operate an aircraft faster than 250 knots when below 10,000 feet MSL, regardless of the type of airspace. When operating below 2,500 feet AGL and within 4 nautical miles of the primary airport of a Class C or D airspace area, the maximum airspeed decreases to 200 knots. This 200-knot limitation also applies to aircraft operating in the airspace below the lateral limits of Class B airspace and in a VFR corridor designated through such airspace. Another major classification of airspace is called special use. You are required to either avoid these areas or to abide by certain limitations within them. For example, flight within prohibited areas is not allowed because of national security or other national welfare reasons. In contrast, flight within a restricted area is not prohibited, although certain limitations may be imposed due to hazards in the area. To fly through this area, you must receive authorization from the restricted area's controlling agency. Warning areas are over coastal and international waters and cannot be designated as restricted. However, the activities within these areas may be as hazardous as restricted areas. Military operations areas are blocks of airspace in which military training or other military maneuvers are conducted. VFR pilots should exercise extreme caution when flying within an active MOA. An alert area usually contains a high volume of pilot training or an unusual type of aerial activity. Flight within alert areas is not restricted, but you are urged to exercise extreme caution and watch for other traffic. Controlled firing areas contain activities which, if not conducted in a controlled environment, could be hazardous to non-participating aircraft. However, when a non-participating aircraft is spotted approaching the area, all activities are suspended. The final grouping we will look at is designated as other airspace areas. The first type of airspace that falls under this classification is called an airport advisory area. There are 3 different types of advisory service available at select airports. The FSS provides a local airport advisory, or LAA, service to all participating aircraft within a 10 statute mile radius at airports that have a flight service station but don't have an operating control tower. Although your participation is not mandatory, the flight service station gives valuable information about known traffic, wind direction and velocity, the altimeter setting, and the favored runway. Remote Airport Advisory, RAA service is provided within 10 miles of busy general aviation airports that do not have an operating control tower, or FSS, located on the airport. The Airport Facility Directory lists RAA locations and times of operations. The third service available in an advisory area is Remote Airport Information Service, RAIS. This service is used for short-term special events like medium-sized fly-ins to provide pilots with known traffic updates and special instructions. Service notification is given through a NOTAM D. Military training routes are also defined as other airspace. These routes are developed for the purpose of conducting low-altitude, high-speed military training. You should be aware that operations in excess of 250 knots may occur on military training routes below 10,000 feet MSL. You should also be familiar with Terminal Radar Service Areas, or TRSAs. TRSAs have been designated at certain Class D airports to provide radar service for participating VFR aircraft. You are encouraged to contact ATC, but it is not mandatory. The dimensions of TRSAs are depicted on sectional charts. Temporary flight restrictions, or TFRs, also come under the category of other airspace. TFRs are issued by NOTAM when necessary to protect persons or property on the ground or in the air, maintain air safety, or prevent congestion around aerial demonstrations or major sporting events. TFR NOTAMs are typically issued 30 days prior to the event and typically include effective dates, times, and geographic features or coordinates of the restricted airspace. Other types of airspace in this classification are parachute jump aircraft operations and flight limitations or prohibitions. The days of having the sky all to yourself may be gone, but your freedom is not. The different categories of airspace and the regulations that go along with them are designed to make flying safe. By understanding the requirements of each type of airspace, you'll soon realize that you have a great deal of freedom to operate in the national airspace system.
Continental 420, clear to land 35 right.
Warrior 11 Delta, descend and maintain 4,000.
2 Mike, taxi to Alpha.
King Air 8 Tango Charlie, cleared for takeoff. 33 Golf, 1 ample right turn.
How can so many aircraft operate this smoothly? Without the essential services of radar and air traffic control, the skies around most airports would be hopelessly clogged. This program introduces you to the common facilities found at controlled airports and explains how you, as a VFR pilot, can efficiently use the services they provide. We'll also expand on the communication skills needed to fly into and out of areas where an authorization from air traffic control is required. Let's begin with a look at transponders. Transponders are an integral part of the ATC radar beacon system. They enhance the identification of aircraft and help controllers provide better separation. The process begins when a radar antenna sends out a discrete interrogation signal. This triggers a reply from your transponder equipment. The reply is decoded and displayed on the controller's screen as a distinctive blip. The display of information on the screen depends on what you have set on your transponder. This knob turns your transponder on and off. When it is turned to the standby position, the unit is on, but it doesn't reply to interrogation signals. This position helps the transponder warm up before you need to use it. Sometimes the controller may ask you to select standby to reduce the clutter on the radar screen.
Cessna 241, squawk standby.
When you select on, the transponder begins to reply to interrogations from radar sites. This setting is sometimes referred to as the normal or Mode A setting. The altitude or Mode C setting is selected by turning the knob to ALT. If your aircraft has automatic altitude reporting equipment, your altitude will be displayed on the controller's screen. This light is called the reply monitor light. It flashes every time the transponder replies to an interrogation. It's a good indicator that the transponder is working. You can also test the transponder operation by pressing the test button. If the transponder is functioning properly, the reply light will light up. The ident button is used to help the controller identify your aircraft. When you press it, a signal is transmitted that causes your display to blossom on the radar screen. When you hear the controller say,
Cessna 241, ident.
Press and release the button. Never ident unless you receive a request from ATC. These windows are used to select the appropriate transponder code. Some codes are assigned by ATC, while others you select yourself. The codes and procedures for selecting them are covered in your textbook. Let's turn our attention now to the operating procedures at an airport with a control tower. We'll include some of the typical communications that occur during departure and arrival. The number of controllers varies from one tower to the next. Each person has a specific duty or position and, generally, controls one frequency. One of these positions is ground control. This person issues taxi instructions to aircraft moving to and from the active runway, as well as from one point to another on the ramp. Before you taxi from the parking area, you need to get an authorization from the ground controller.
Most communications can be divided into just 4 basic elements.
Jeffco Ground, Cessna 52241 at the General Aviation Ramp, ready to taxi for takeoff.
The ground controller will tell you to taxi to the runway in use and provide you with existing wind information, the altimeter setting, and any pertinent remarks. At a busy airport, a tremendous frequency congestion would occur if the controller repeated this information to every pilot requesting a taxi clearance. To relieve this, many large airports have a specific frequency for recorded airport information, known as Automatic Terminal Information Service, or ATIS. Each time the recording is updated, it is given a new phonetic letter for identification.
Sutton Airport Information Delta, 1245 Zulu weather, temperature 85, dew point 47, wind 120 at 13, altimeter 3007. Landing and departing runways 17 left and 17 right. Advise the controller on initial contact you have information Delta.
Airports with a high volume of traffic may have a position called clearance delivery. It's primarily an IFR service, but can be used by VFR pilots to help improve the coordination of departing traffic. The controller provides you with a heading, altitude, transponder code, and departure control frequency to use after takeoff. If you want to use clearance delivery, contact the controller after listening to ATIS and before calling ground control. Inform the controller of your aircraft type, direction of flight, and that you have listened to the ATIS information.
Ashland Clearance Delivery, Warrior 81312, with Information Hotel, VFR northbound. Warrior 81312, after departure, fly runway heading, maintain 3000, squawk 4505. Departure frequency will be 124.6. Contact ground 121.9er.
When you contact ground control at an airport that does not have a clearance delivery but provides radar services to VFR pilots, you should include the direction of flight or your destination. In this situation, the ground controller will give you a transponder code and departure frequency.
Sudden ground, Cessna 62740 at the general aviation ramp, ready to taxi 17 left, VFR southeastbound with information Delta.
Cessna 740, taxi to runway 17 left. Departure frequency will be 119.3, squawk 1120.
With this clearance, you are authorized to cross all taxiways and runways on your way to 17 left. But it does not authorize you to cross or taxi onto the assigned takeoff runway. Once the pre-takeoff checklist is complete and you're ready to depart, taxi up to the holding line, switch from the ground control to the tower frequency, and let the tower controller know that you are ready to take off. Be sure to give your direction of flight or destination.
Sudden tower, Cessna 62740, 17 left, ready for takeoff, VFR southeastbound.
If other airplanes are in the process of landing, the controller will advise you to hold short. This means that you are not authorized to taxi onto the runway and should remain at the holding line. When the final approach path is clear, the tower might ask you to taxi into position and hold. This authorizes you to taxi onto the runway and line up on the center line for takeoff. At the appropriate time, the tower controller will clear you for takeoff.
Cessna 740, runway 17 left, cleared for takeoff.
Cessna 740.
When you receive a clearance with the word immediate in it, you should follow the instructions without delay.
Warrior 312, cleared for immediate takeoff.
Where radar is available, the controller may request that you contact departure control.
Cessna 740, contact departure control.
Because you are being handed off from the tower to departure control, the controller is expecting your transmission. Thus, your initial contact is very brief.
Sudden departure, Cessna 62740, climbing through 6,000 for 7,500.
Cessna 740, ident.
The controller will let you know that he has identified your aircraft and will provide you with appropriate instructions.
Cessna 740, radar contact. Report reaching 7,500.
You are strongly encouraged to use VFR radar services when available because of the added safety provided. The level of service varies with the type of facility. Basic radar service provides participating VFR aircraft with traffic advisories and limited vectoring. The controller may help you spot traffic by letting you know its approximate location relative to your airplane. Other radar services, such as sequencing and separation, are used at busy airports to help controllers guide both IFR and VFR aircraft smoothly. When a controller issues a traffic advisory, it is given in relation to a 12-hour clock, with 12 o'clock aligned with your ground track. For example,
Cessna 740, traffic 1 o'clock, 2 miles. A Cessna 7,500, eastbound.
if you are turned into the wind to maintain your ground track, the actual location of the traffic may be different than that given by the controller. In this example, the traffic is actually at your 2 o'clock position. When you're trying to locate the reported traffic, consider your ground track and encompass a wider range in your scan. Let the controller know whether or not you have spotted the traffic. If you don't see the traffic, tell the controller negative contact and continue to look. Keep in mind that traffic advisories do not relieve you of the responsibility of maintaining your normal scan for collision avoidance. When you leave the radar coverage area, the controller will let you know that the service is no longer being provided and will have you reset your transponder for VFR flight.
Cessna 740, radar service terminated. Resume your own navigation, squawk 1200.
Now let's turn our attention to some of the procedures and communications for an arrival at a controlled airport. If you're arriving at an airport with an operating control tower, it is a good practice to make your initial call-up approximately 15 miles from the airport. Before you enter Class D airspace, you must establish and maintain radio communications with the tower. A clearance from ATC is required before you enter Class B airspace. Your initial call-up should be outside of the Class B boundary and over a designated visual checkpoint. These points are shown on aeronautical charts and will be covered in depth in the section on charts. If you're approaching an airport in Class C airspace, you must establish two-way radio communications with ATC before entering the outer circle. You are strongly encouraged to make the initial call within the outer area. Let's take a closer look at the procedures for entering Class C airspace. Listen to the ATIS as you approach the 20-mile outer area.
Jensen Airport, information Sierra. 1445 Zulu weather, temperature 76, dew point 44, wind 160 at 1.
Plan your approach so that your initial contact with ATC can be made when you are above a designated visual checkpoint or prominent landmark.
Jensen approach, Cessna 62740, over Prospect Reservoir at 8,000 with Sierra, landing Jensen.
Cessna 740, stand by.
Since the controller used your call sign, radio communications have been established. This means you can continue on course and enter the Class C airspace. If the controller uses the words,
Aircraft calling Jensen approach, stand by.
Radio communications have not been established, and you must remain clear of the Class C airspace.
In most cases, the controller will give you a transponder code and ask you to ident.
Cessna 740, radar contact, 23 miles northeast of Jensen, turn left, heading 220 for left base, runway 17.
As you near the airport, approach control will let you know when or where to contact the tower.
Cessna 740, 5 miles northeast of Jensen, contact the tower 119.9er.
Cessna 740, tower on 119.9er. Jensen Tower, Cessna 62740, 5 miles northeast for left base runway 17.
At airports with an operating control tower, you must obtain a clearance to land.
Cessna 740, cleared to land, runway 17.
You may also receive additional instructions after landing.
Cessna 740, next available taxiway, contact ground, point 7.
Cessna 740, roger. Jensen ground, Cessna 62740, clear of 17 at Alpha 1, request clearance to General Aviation Ramp.
Cessna 740, taxi to General Aviation Ramp via Alpha.
As you gain experience, your knowledge and understanding of the ATC system will grow. You'll discover how easy it is to communicate effectively with air traffic controllers, and you'll learn to make efficient use of the services provided by ATC and radar.
Douglas traffic, Cessna 52241, taxiing to runway 28 at Douglas.
Colby traffic, Warrior 81312,
taking off runway 17, departing to the southeast at Colby.
Denver Flight Watch, Cessna 52241, Hugo VOR, over.
Your radio allows you to communicate both with ground facilities and with other aircraft. Its proper use is important for smooth operations within the nation's airspace system. Although communicating by radio may be a new experience for you, you will quickly become familiar with the terminology and the format. After a brief look at some of the unique characteristics of radio communications, we will concentrate on some sample transmissions which relate to uncontrolled airports. A phonetic alphabet is used to reduce the confusion between letters that sound alike. For example, the letters E and P sound very similar, so the words echo and papa are used to represent these letters. 9 is the only number pronounced differently. It is said as niner.
The key to good radio communications is to be prepared and brief. Most communications can be divided into just 4 basic elements. Identify the facility you are calling. Identify yourself. State the message or request. Conclude the transmission. Let's take a closer look at these elements. When you identify the facility, you may be speaking to someone who is operating a ground-based radio, or you could be addressing other pilots in the area. When you identify yourself, use the full registration number of the airplane. Precede this number with either the aircraft type, model, or manufacturer's name. You would identify this airplane as Cessna 52241. Sometimes a shortened version of the registration is used, but you should not shorten it yourself. Wait until the person you're talking to does it first. Your message or request lets others know your location and your intentions. To conclude your transmission, you may use the word over to indicate you are waiting for a response, or Roger to indicate you have understood the message. If the status of your communication is obvious, no conclusion is needed. Use these 4 elements to help organize your thoughts and decide what you're going to say. Write the message down if necessary, but be brief and to the point. When you're ready to talk, be sure the radio is properly tuned to the desired frequency, as discussed in the textbook. Then listen to be sure you won't interrupt another call. When the frequency is clear, hold the mic directly in front of your mouth and push the transmit button. Speak clearly and use a normal conversational tone. When you're finished, release the button and listen for a response. Let's turn our attention now to general radio procedures. At each uncontrolled airport, one specific frequency is used to communicate your intentions or to receive information. This frequency is called the Common Traffic Advisory Frequency, or CTAF. You should continuously monitor and use this frequency when operating to or from an uncontrolled airport. It is very important to remain alert and continue to scan for other aircraft, since they may not be radio equipped and some pilots might not use the frequency. There is no substitute for the see and avoid concept. By using the appropriate CTAF and applying good operating practices, you can enhance safety around uncontrolled airports. For example, during the approach, make your initial call approximately 10 miles from the airport. When you reach the traffic pattern, continue to announce your position by reporting downwind, base, final, and when you are clear of the runway. In a similar manner, when you depart an uncontrolled airport, announce your intentions before you begin to taxi and before you taxi onto the active runway. Let's look now at some examples of how to use the Common Traffic Advisory Frequency. At an airport with no ground-based radio facilities, the CTAF will be multicom, and you will transmit on 122.9er. Since there are no ground facilities with this service,
You will make your call to any aircraft operating in the area. Your initial call in this case is
Baker traffic, Warrior 81312, 10 miles south, 4,500, landing Baker.
When you reach the airport, continue to announce your position in the traffic pattern.
Baker traffic, Warrior 81312, entering left downwind, runway 29er, Baker. Baker traffic, Warrior 81312, turning left base, runway 29er, Baker. Baker traffic, Warrior 81312, turning final, runway 29er, Baker. Baker traffic, Warrior 81312, clear of runway 29er, Baker.
When you depart an uncontrolled airport, the calls will be
Baker traffic, Warrior 81312, taxiing to runway 29er, Baker. Baker traffic, Warrior 81312, taking off on runway 29er, departing southwest, Baker.
At other airports, the common traffic advisory frequency may be Unicom. This is a privately operated radio station that may provide wind and runway information. In this case, your initial call will go to the Unicom operator.
Mansfield Unicom, Cessna 52241, 10 miles east, descending through 6,000, landing Mansfield. Request wind and runway information for Mansfield. Over.
If there is an operator on duty, the typical reply will be
Cessna 241, Mansfield Unicom, wind 110 at 5, favored runway is 09er.
The Unicom operator is not a controller. Therefore, you would continue to announce your position to Mansfield traffic, just as in the previous example. Let's turn our attention now to communicating with a flight service station. An FSS provides a variety of services that you can access through your radio. Some of these include opening and closing a flight plan, weather updates, and at certain locations, airport advisories. When you communicate with an FSS, you normally precede the call with the word radio. A flight service station operates on a number of frequencies. Sometimes you can communicate and receive the reply on the same frequency. At other times, you may want to communicate on one frequency and receive on another, such as a VOR. During your initial call to an FSS, specify the frequency or facility you are listening to before you state your message or request.
Casper Radio, Warrior 81312, receiving Worland VOR. Over.
At an airport with a non-automated flight service station and no control tower, the FSS usually provides airport advisory service on a CTAF frequency of 123.6.
Scottsbluff Radio, Cessna 52241, ready to taxi, VFR westbound, request airport advisory.
Cessna 241, Scottsbluff Radio, wind 280 at 6, favored runway 30, altimeter 299er5. No reported traffic.
Talking on the radio is a skill that requires practice and a sound knowledge of basic radio communications procedures. As you gain experience and explore the variety of services that are available, you will find that your confidence as well as safety will increase.
When you plan a flight, it's essential you use the most current information available. This program introduces the common reference sources used for flight planning and briefly explains how to interpret them. The sources we'll look at are the Federal Aviation Regulations, the Aeronautical Information Manual, Airport Facility Directory, Advisory Circulars, and Jeppesen Pilot Resource Services. Some of these publications give you very specific information, while others give general operational data. Let's begin with one which contains specific information, the Federal Aviation Regulations. A few of the areas you should be familiar with are Part 1, Definitions and Abbreviations. Part 61, Certification of Pilots and Flight Instructors. And Part 91, General Operating and Flight Rules. Due to the ongoing changes in the FARs, it's important that you have access to current editions and review them periodically. Another publication you should be familiar with is the Aeronautical Information Manual, or AIM. This publication is your official guide to basic flight information and ATC procedures. It covers a wide range of topics and helps keep you informed about operating in the National Airspace System. Let's look at some of the items of particular interest to VFR pilots. The chapter on navigation aids describes, in detail, the various types of facilities that are available to both VFR and IFR pilots. For example, the section on VORs explains the frequency range of your VOR receiver and tells how to check its operation. If you plan on flying after sunset, you should be familiar with information in the chapter on aeronautical lighting. Things like specific airport and obstruction lighting are explained in detail. The different types of airport markings and signs are also covered. The chapter on airspace describes the various forms of controlled, uncontrolled, and special use airspace and their operational requirements. Since portions of this chapter are changed frequently, it's a good idea to review it periodically. The Air Traffic Control chapter contains a section on radio communications. It explains the terms and phrases used by pilots and controllers during ground and flight operations. Another section, entitled Airport Operations, explains the correct procedures for operating on or near an airport. The Emergency Procedures chapter contains valuable information regarding the authority and responsibility of the pilot in command, the services available from air traffic control, distress and urgency procedures, and rules governing two-way radio communications failure. The AIM also covers several medical facts that relate to pilots, such as the effects of alcohol, over-the-counter medication, high-altitude flight, and vision and illusions in flight. The Pilot Controller Glossary is an important supplement to the AIM. It provides definitions for most of the terms used in the ATC system. When everyone uses the same language, misunderstandings are minimized. Now let's look at the Airport Facility Directory. This publication contains facts about all public-use airports, heliports, and seaplane bases. It is published in a number of volumes, with each one covering several states in a given region. To help explain the contents, let's look at some typical entries from the Southwest Directory. Each volume has a directory legend that helps you interpret the abundance of information. As you gain more experience in using the Airport Facility Directory, you'll find the entries easy to read. For example, here is the listing for Centennial Airport, which is one of several airports in the Denver area. We won't cover every entry in this listing, but we'll look at a few items that are pertinent to VFR operations. Centennial Airport is located 3 miles southeast of the city of Denver. This gives you a general area in which to look for the airport as you approach the city. The elevation of Centennial is 5,883 feet. This is useful for determining such things as the traffic pattern altitude, the upper dimension of the Class D airspace, and the accuracy of your altimeter. The letter B indicates that Centennial has a rotating beacon. This information can be very helpful when trying to locate the airport at night. These entries show the services which you can obtain at Centennial. S4 means major airframe and power plant repairs are available. If your airplane develops mechanical problems, you can get it fixed at this airport. The types of aviation fuel available are 100 low lead and Jet A. This information is important when you select an airport for a fuel stop. OX means oxygen, and the numbers refer to the types of recharging or replacement services available. Runway data are also covered in this section. In addition to basic dimensions and lighting, it includes specific information about each runway. Runway 17 right, for example, has a right-hand traffic pattern. This is a very important fact that helps you anticipate pattern entry instructions from the controller. Obstructions are also listed, such as the pole on the approach end of runway 35 left. The airport remarks section contains operational information about the status and usability of the airport. For example, there is a caution about waterfowl on and near the airport. As you approach or depart the airport, you should remain alert for bird activity. A bird strike can severely damage an airplane. Some of the additional remarks that relate to Centennial are that the airport is attended continuously. There are men and equipment working on Ramp A, and there are noise abatement procedures. The remaining sections of the directory listing for Centennial include weather data sources, communications information, and a listing of the various radio aids. Under the listing for the Denver VORTAC is a note to see the special notices. This section of the airport facility directory covers a wide variety of subjects that might affect your flight. Here is the entry referred to in the listing for the Denver VORTAC. The DME feature of the VORTAC may not be usable due to an overload of interrogations. This may influence your ability to use DME to locate Centennial Airport. A list of parachute jumping areas is included in another section of the airport facility directory. A section that should always be checked before a flight is the Aeronautical Chart Bulletin. It lists the changes that have occurred since the last printing of your aeronautical chart. Another method of supplying you with time-critical flight planning information is through the Notices to Airmen system, or NOTAMs. There are three basic types: NOTAM Ds, NOTAM Ls, and FDC NOTAMs. NOTAM Ds cover such items as inoperative nav aids or runway closures at all public use airports. These NOTAMs are distributed from the National Communications Center. NOTAM Ls cover things like taxiway closures, ramp closures, and mowing operations, and are distributed only by local flight service stations. FDC NOTAMs are more likely to affect you when you get into more advanced flying. They usually amend instrument approach procedures and instrument charts. You can get NOTAM information from a flight service station, a computer briefing service, or the Notices to Airmen publication. Let's turn our attention now to another source of aviation information, the Advisory Circular, or AC. Advisory circulars contain information and procedures which are necessary for good operating practice, but which are non-binding unless they're incorporated into a regulation. ACs range in size from a single-page document to full textbook length and are issued as the need arises. They are numbered to correspond with the various FAR parts and subchapter titles. For example, the general subject number 60 pertains to airmen, and a specific number within the 60 series, such as 61, identifies subjects relating to the certification of pilots and flight instructors. One of these ACs, 6112, answers many of the questions you might have prior to or during your flight training. Knowing the general subject numbers will enable you to find ACs on a given topic much easier. A listing of all the ACs and their current status can be obtained from the Advisory Circular checklist. Also included in this checklist is a listing of FAA publications sold by the Government Printing Office. A couple of these are the FAA Computerized Testing Supplements and the Practical Test Standards. You can order a free copy of the AC checklist from the address listed at the beginning of the AIM. Jeppesen Pilot Resource Services provide excellent reference sources. They combine many of the features found in the AIM and Airport Facility Directory into one publication. In addition, they include all of the pertinent FARs. The loose-leaf format allows you to easily insert revisions, which makes them some of the most current publications available. Let's take a look at some of the service features. Jeppesen Pilot Resource Services are divided into several subject areas. Common information is grouped together and identified by divider tabs for easy reference. For example, the section on air navigation radio aids presents detailed information about the types of navigational facilities available. A comprehensive GPS LORAN coordinate directory contains latitude and longitude coordinates for airports, nav aids, and waypoints. Airport locations include an FAA airport identifier, as well as the airport reference point coordinates. Another listing gives airports by the three-letter identifier. Navigation aid locations are also listed by name and identifier. Waypoint locations are listed by name. A unique feature of Pilot Resource Services is the FAR component. It provides the regulations pertinent to a wide variety of operations, including hazardous materials carried by aircraft and the National Transportation Safety Board regulations. Another very helpful component of Pilot Resource Services is the Airport Directory. It lists over 6,000 civil and military airports that are open to the public. In addition to the normal airport data, VFR entries contain an airport diagram to help you recognize the airport more easily from the air. Only the pertinent operational data is included for IFR airports, since detailed charts are available in Airway Manual Service. You might think of the airport directory as an airport facility directory with pictures. This program has provided a brief overview of the sources of flight information used during your pre-flight planning. It is your responsibility, as pilot in command, to familiarize yourself with every aspect of the flight and to ensure your planning is based on the most current information available.